teachers and scientists have a vital role in solving. We will also discuss the education sector in chemistry, which is set to see strong expansion globally due to government support and incentives. Also, to include quality education, which leads to growing importance of education, technological, and pedagogical changes in teaching and learning. The objective of this international webinar is to present the frontier areas in research and toward excellence in education in India in the 21st century, looking into the challenges and opportunities. The webinar program includes talk by Dr. James Barton, who is an educational consultant, Ireland, and ex-staff member of Chemistry Department at Wilson College. Dr. P. Ramasamy, Computational Chemistry Group, University of Mauritius. Professor Dr. G. Ramakrishnan, President of the Chromatography Society of India. Dr. Chandrakant Gadipille, Assistant Professor of Israel Institute of Technology. Dr. P.K. Bakshi, Vice Chancellor of PDM University, Bahadurgarh, Haryana. We also have two of our alumnus, esteemed alumnus from USA, who will be sharing this platform. The response of this participant of this webinar has been mind-blowing. I'm pleased to put on record that over 2021 participants registered, including participants from UK, USA, Malaysia, Ethiopia, and China. I'm confident that this webinar will indeed bring a lot of interest among all of us to explore and pursue the area of research, thereby developing our society as a whole. I wish all the delegates a very happy, memorable, scientifically and academically stimulating time in Wilson College online platform. Thank you very much. Over to Dr. Muskin.
Thank you, madam. Now I call upon our dynamic leader who always encourages, supports, and motivates the staff and under whose leadership college is progressing by leaps and bounds. She is none other than our beloved principal, Professor Anna Prabhu. I request madam to say a few words about college and webinar. Over to you, madam.
Thank you very much. A very good morning and warm greetings to distinguished speakers or delegates from Wilson College in the name of Almighty. It is my proud privilege to welcome all the dignitaries, guests, resource persons, and all the participants to this two-day international webinar, Emerging Trends in Chemistry Education and Research, organized by one of the oldest departments in the University of Mumbai, the Chemistry Department of Wilson College. Wilson College is one of the oldest educational institutions since 1832, founded as Ambroli School in Girgaon by Reverend Dr. John Wilson at his residence. A collegiate section, which was later called Wilson College, was added in 1836. Focusing on holistic and inclusive education, it catered to the educational needs of boys and girls from all castes, communities, religions, and strata of society. Lessons were conducted in both English and vernacular languages. Wilson College contributed significantly in pre-independence era. I am proud and privileged to be the principal of historically significant college with a glorious past and bright future. Today, Wilson College is one of the few colleges that offer several self-financing courses. It is a multi-faculty college that offers education in arts, commerce, science, management, and media at both graduate and undergraduate level. It is also a center for research in several disciplines. We are now in our fourth NAC cycle and have a consistently A grade. Through the many changes and challenges that have rightly taken place in this 200-year-old institution, the vision and guiding principle have remained to produce intellectually well-trained, morally upright, socially conscious, and spiritually oriented men and women. Though being a Christian minority institute, we at Wilson have always focused on the mission to impart holistic and inclusive education to students of all castes, communities, religion, and strata of society. Being a staff member from chemistry department, My vision for the science department is to have state-of-art laboratories and research facilities. My efforts are also to make the DST FIS facility a national center for researchers and to help all departments to grow by producing quality research papers, acquiring major and minor research projects, organizing national and international conferences, generating funds through IPR and industrial consultancy, and contribute in nation building. This international webinar is one of the steps towards achieving this goal. My vision for the college is to see it features in national ranking within the top 10 institutes of India. A challenging task indeed, but we at Wilson College will achieve this landmark together. I am happy and confident that all my colleagues are supporting the management and principal in our pursuit of imparting quality education and producing world-class graduates and postgraduates for the country as envisioned in our college motto. International Chemistry Webinar on Emerging Trends in Chemistry Education and Research is a global standard 2 days webinar which will serve as a great platform to discuss and learn about latest advancements and novel approaches in chemistry research. It aims to bring together leading academic scientists, research scholars, and students to exchange and share their expertise, experiences, and research results on all aspects of chemistry and related fields. This 2 days webinar will also inculcate research aptitude among student community and will provide a premier interdisciplinary platform for researchers and educators to discuss the most recent innovations, trends, and concerns, as well as practical challenges encountered and solutions adopted in the field of chemistry post-COVID-19 pandemic. International Chemistry Webinar on Emerging Trends in Chemistry Education and Research 2020 will also discuss the education sector in chemistry, which is said to see strong expansion globally due to the government support and incentives, and inclusion of quality education as one of the key sustainable development goals of India, which led to growing importance of education and technological and pedagogical changes in teaching and learning. Though the country is under lockdown, but we at Wilson have been organizing many FDP workshops, webinars in association with Pandit Madan Mohan Malviya National Mission on Teachers and Training and University of Mumbai International National Webinars on varied topics, faculty enriching programs, student enriching programs, motivational, educational, skill-oriented online programs for student community, and many more. I am indeed happy and proud to say that almost all the departments of the college have organized some other program during this lockdown period and vacation to keep themselves away from anxiety and engage in some fruitful and meaningful discussions. I wish the organizers all success in conducting this online international webinar on emerging trends in chemistry education and research, which has seen around 2021 registrations from the world, including participants from UK, USA, Malaysia, Ethiopia, and Wuhan, China. I hope that it will serve as a platform for the exchange of innovative ideas and research collaborations between various institutions and also at individual level. It will inspire the young minds. I am confident that this international webinar will invoke a lot of interest among the teachers and encourage them to explore and pursue the area of research, thereby helping our society as a whole. I appreciate the efforts of staff of chemistry department, the HOD, and all the organizing members of Wilson College and Association of Chemistry Teachers and University of Mumbai for their support, who have worked in concerted and cohesive manner and have managed to pull the best resource persons for the deliberations. It is indeed my honor to inaugurate this international webinar, and I wish all the participants a very happy, fruitful, memorable, and scientifically stimulating webinar. I wish you all a good day. Over to Dr. Maske.
Thank you, madam, for your encouraging word. This webinar is possible due to your encouragement only. Now, I request Dr. Devi Prabhu, who serves as a teacher the head of the department, and later as the adjunct professor of chemistry department in Wilson College for almost 5 decades. He is a fellow of Royal Society of Chemistry, London. He has represented India in 5 international chemistry and junior science Olympiads. He received Best Teacher Award by Chemical Research Society of India in 2006. He has guided 8 students for PhD and has more than 50 research papers to his credit. He is a general secretary and founder member of a Association of Chemistry Teacher. I request Dr. Prabhu to say a few words. Over to you, Dr. Prabhu. Prabhu sir. Chetan. Hello, Chetan. Prabhu sir. Unmute you.
पार्टिसिपंट्स मध्ये गेले सर एक मिनिट
Oh.
आलेत सर परत सर प्लीज अनम्यूट युअर सेल्फ प्रभु सर प्लीज अनम्यूट युअर सेल्फ यस
Hello, Prabhu sir.
Hello, sir is already in the panel group. Chetan, please connect, sir.
Prabhu sir is unmute. Hello, Prabhu sir.
सर बोलिए सर सर अनम्यूट हाँ अनम्यूट यस सर
Hello, Prabhu sir.
Hello. Yes, sir.
Hello.
Yes,
Hello,
sir.
sir.
Sir, we can hear you, sir.
Hello.
Yes, sir, we can hear you.
Can you hear me?
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Yes, sir.
Hello.
Yes, sir, we can hear you.
Yes, sir. Sir, we can see you as well as we can hear you.
Voice is very low. I can't listen. I can't hear also.
Sir, but you speak.
Your audio is very low.
Mr. Chetan, please do the needful.
Hello.
Hello, we can hear you, sir.
सर बात कीजिए सर आपका आवाज आ रहा है सर
Prabhu, sir.
Good morning,
Yeah.
dear friends. At the onset, I congratulate Principal Dr. Anna Pratima Nikalje, Professor Sakina Butwala, and all her chemistry colleagues for conceptualizing and organizing this international webinar. The chemistry department of Wilson College is one of the oldest chemistry departments in our country. It started in 1887 and in 1917 started research almost 100 years back. It has been a very active teaching department and good research in several fields like colloid chemistry, reaction kinetics, coordination chemistry, environmental chemistry, and catalysis. Chemistry has always been at the center of mankind's progress, and its progress has always been exponential. Over the last few years, chemistry has given us several new novel compounds with exciting properties. Just to say, fullerenes, superconductors, composites, novel catalysts, etc. Progress in instrumentation like chromatography and spectroscopy enables us to detect materials right up to femtogram level. What are the challenges before the chemist? One is synthesis of new drugs to overcome diseases, harnessing new sources of energy, especially nuclear fusion, development of environment-friendly processes using green reagents and solvents, and synthesis of biodegradable plastics. And very importantly, conversion of waste into energy and biogas. It is gratifying to note that in India, we have a large enrollment for chemistry, especially at undergraduate and postgraduate student levels. We also have several world-class research institutions where research in frontline chemistry is going on. And I'm very happy that in this webinar, 4 international experts are there to talk on their areas of expertise. Professor Ramasamy, my good friend, Professor G. Ramakrishnan, Dr. Chandrakant Gedipalli, and Professor A.K. Bakshi. I am indeed very glad that Dr. James Barton, my former colleague in chemistry department of Wilson College, will be the chief guest. And 3 of our very distinguished alumni will be participating, namely Dr. Chandrakant Gadipalli from Israel, Professor Reji Nair from US, and Dr. Sham Rele from US. I extend to these 3 alumni a very warm welcome. Association of Chemistry Teachers is the national registered body of chemistry teachers. Since its inception in 2000, it has been engaged in several activities to promote excellence in chemistry, like national and international conferences, national and international chemistry olympiad, and training workshops for students, teachers, and industry chemists. GB Globalized Research Journal of Chemistry is also one of the sponsors of this webinar. Mr. Rajan Pendurkar is a publishing coordinator of this journal, which is supported by Association of Chemistry Teachers. This journal is abstracted in Chemical Abstracts USA and has a ISI impact factor 0.883 and does not charge any fees for publication of papers, because we believe research should be an activity which should be available to everybody, and payment should not be the criteria for publication of papers. I am told this webinar has a very good enrollment, more than 2,000 participants from US, Malaysia, China, UK, Ethiopia. I would like to congratulate the chemistry department on this wonderful achievement, and I wish the seminar grand success. My special thanks to all the organizers, the eminent faculty, and the chief guest, Dr. James Barton. Thank you very much.
Thank you, sir, for your guidance and support and help. Without your help, today's webinar would not have been possible. Thank you once again. Now, I request Dr. Ashish Usgare, Assistant Professor, Chemistry Department, to host the further proceedings. Over to Ashish Usgare.
Thank you so much, Dr. Maske. A very, very warm good morning to one and all. And I welcome once again all the participants and all the dignitaries for this 2-day international webinar on emerging trends in chemistry education and research. It's my proud privilege to introduce to all of you today the chief guest of this function. He is none other than a very, very popular former staff of Wilson College and a very eminent personality, Dr. James Barton. Dr. James Barton completed his chemistry education from the Queen's University, Belfast, Ireland in 1960. He did his PhD in transition metal hydrides from the Queen's University in 1963. He taught chemistry at the Campbell College, Belfast, Ireland from 1963 to 66. Dr. Barton had a calling to serve in India, and therefore he came to India in 1966 and taught chemistry at the Serampur College, Kolkata from 1966 to 69. Then was his stint at Wilson College, Mumbai, where he taught inorganic chemistry from 69 to 77. He joined the department under the leadership of the then head of the department, a very famous personality, Professor Naber sir. Dr. James Barton, a curious mind, never stopped studying. In 1976, he completed a very well recognized diploma, which is very popular and famous in the European countries, the DAYS, that's the Diploma in Advanced Studies in Education, from the University of Ulster, Coleraine, Ireland in 1976. Dr. Barton always wanted to be with the young minds, and therefore, in 1977, he left Wilson College to join the very, very famous Woodstock School, Missouri, in Uttar Pradesh, and taught chemistry there till his retirement. Dr. Barton leads a very, very active retirement life, and he is an educational consultant at Belfast Island, where he resides now. Before settling in his native country, Dr. Barton helped many schools for their setups to begin the international education, to name one of the famous school, the Pinto Group of Schools in Goa. At Wilson, Barton sir had many, many things for his credit, to his credit and achievement. At Wilson, he pioneered the semi-micro qualitative analysis. This method developed by him was adopted by the University of Mumbai and was implemented in all the affiliated colleges. With the help of his colleagues in the department, he even went on to prepare a college practical manual incorporating the very famous semi-micro qualitative analysis. Friends, today we talk about different pedagogies of teaching. Way back in 1960s, Dr. Barton initiated the group discussion method of learning. Not only that, he himself was instrumental in providing the study material to the students along with making arrangements for the classroom. We all know how difficult it is nowadays to perform extracurricular activities because infrastructure classrooms is a major concern. This self-learning method of the students involved twice a week the students gathering together. He encouraged students to undertake projects as a part of experiential learning. Now, that's again another pedagogy that we try to adopt and implement nowadays about self learning, experiential learning. Dr. Barton practiced this, introduced this way back in 1966. He is a very good motivator. He motivated all the younger staff and students to develop the reading habit, and not only that, being very, very generous with his own personal copies of books that he gave to all the students and teachers. I remember Prabhu sir sharing with me that after donating his books, after giving his books for learning, Dr. Barton did not ask for the books back, but then he quietly informed Prabhu sir about it, and Prabhu sir did the needful in getting back the books to him. Dr. Barton has a very, very great personality, and thus he got a free hand from the then management, because of which he was able to contribute richly to Wilson College and to the students' community in general. Dr. Barton is a very ardent sports fan, and aptly, he was also appointed as the vice president of the very famous Wilson Gymkhana. Ladies and gentlemen, I want your utmost attention to what I'm going to say right now. One of the greatest gifts of Dr. Barton to India, I repeat, one of the greatest gifts of Dr. Barton to India is that he introduced rugby sports to India. And under his coaching, the Indian team at that time went on to be winner twice at international level. Such is the personality of the chief guest of today's function, Dr. James Barton. Ladies and gentlemen, let me present to you Dr. James Barton, and let us hear his message for us this morning.
Dr. Anna Prabhu Nikhalji, Madam Principal, Professor Sakina Butawala, Madam Convener, Dr. Prabhu, my own former colleague, Wilson College, and participants in the international webinar, Emerging Trends in Chemistry, Education and Research. It is for me a great honor to be invited to inaugurate this international webinar. The sense of honor arises from my gratitude for the years I was privileged to be a member of the chemistry department in Wilson College, Bombay University, admittedly in the second half of the last century. At the same time, I am excited because the topic emerging trends in chemistry, education and research is one which is very special to me. Having begun my career as a research scientist in the field of transition metal hydrides at Queen's University in Ireland, my appointment to the Wilson College faculty offered to me unique opportunities to explore the teaching of chemistry in the research-friendly context of Wilson College Chemistry Department. For example, together we pioneered the introduction of semi-micro techniques in the field of analytical chemistry laboratory procedures. The support I received from the then Principal A.J. Bordy, the then Head of Department, Professor J.A. Naber, and my colleagues channeled my enthusiasm for the teaching of chemistry with a view to engaging our students as active participants rather than merely passive recipients of information. The cooperation of the students, for example, in scheduled small group seminars, ensured that they were encouraged to own their own learning. The support of my colleagues and the enthusiasm of the students were very special. That you have invested your time and effort in preparing for the topic today augurs well for teaching and learning in chemistry for the next generation of students. I wish you every success in your discussions facilitated by modern technology. With a deep sense of pride in what you are achieving, I greet you. Jai Hind.
Thank you so much, Barton sir, for inaugurating our international webinar. And ladies and gentlemen, that was Dr. James Barton from Belfast, Ireland. After the formal inaugural program, ladies and gentlemen, we now move to our the session where we have our invited speakers delivering their talk. The first speaker for this morning is a very, very illustrious personality, and he is none other than Ponnadurai Ramasamy. He is from the Computational Chemistry Group, Department of Chemistry, Faculty of Science, University of Mauritius, Republic of Mauritius. Ladies and gentlemen, let me admit that his is one of the most enriching biodata, most achievement-full of biodata that I have ever read in recent times. To give you a brief idea about his achievements, Dr. Ramasamy completed his entire education from India. He did his BSc and MSc degree from the University of Delhi. He achieved his PhD degree in 1996 in physical chemistry from the University of Delhi. He holds many, many prestigious posts. To name a few, he is a visiting professor at the University of Johannesburg. He was awarded the Professor Extraordinaris from the University of South Africa. From 2014 to 2017, he was the visiting professor at the King Saud University. He was appointed in 2012 the professor and the personal chair in computational chemistry. He is on the scientific board advisory of the Organization of the Prohibition of Chemical Weapons, and that's from 2016 to 2021. Dr. Ramasamy is also a research supervisor. 7 students have completed their research and 5 are being supervised under his guidance. He is an ardent researcher. And ladies and gentlemen, the figure that I'm going to quote now is jaw-dropping. He has to his credit more than 224 papers published in ISI peer-reviewed journals. As a researcher, he has many research projects to his credit. 9 research projects so far, out of which 7 have been completed and 2 are ongoing. And the total funding is more than half a crore. He has written a couple of books, to be very precise, 7 books, and all with reputed international publishers. He is also on the editorial board and is one of the editors of the journal Open Chemistry, published by De Gruyters. Friends, Dr. Ramasamy has participated in several conferences, giving keynote address, invited talk, and has also presented oral and poster presentations. He has a vast experience of an administrator on several different bodies. And the list is a very, very long, more than 30. I will just name a few. He is an associate editor of the Research Journal of Chemistry and Environment. He's on the advisory board of the Asian Journal of Chemistry. He's a reviewer of the Research Journal of Chemistry and Environment. Hello, am I audible? Hello, ladies and gentlemen. Hello?
Yes, sir.
Yes,
Yeah.
you're audible. You can go ahead.
Yes. Thank you. He is also the member of the Royal Society of Chemistry. He is an affiliate member of the International Union of Pure and Applied Chemistry. He was the scientific secretary of the IUPAC Satellite Symposium held at the University of Mauritius. He is a committee member at the national level for promotion of science and technology at primary level, conducted by Mauritius Research Council. He is also the Senate member of the University of Mauritius. He is on the High Power Committee member for Scholarship, Ministry of Education, Culture, and Human Resource, Mauritius. Dr. Ramasamy is also an external examiner for the physical chemistry research, and he has examined more than 50 PhD theses. He is also the recipient of the very, very well-known DAD Scholarship. He has received the DAD Scholarship from 2013 to 2012 to 13. Ladies and gentlemen, I am sure by now you would have got a glimpse of what a personality we have this morning. And Dr. Ramasamy is going to talk to us on a very interesting topic. The topic that he has chosen for today is a virtual visit to the home of electrons. Ladies and gentlemen, may I present to you the first speaker of this morning, Ponnadurai Ramasamy. Over to you, sir.
Thank you very much. A very good morning to everyone. I hope you can hear me.
Yes, sir. Loud and clear.
Thank you very much. So, Dr. Gare, thank you very much for the nice introduction. The organizers, the principal of the college, the chief guests, all the speakers, the participants, a very good morning again from Mauritius. Namaste, Bombay, Mumbai. So it's my pleasure to have accepted the invitation, and it's my pleasure to give a talk today on a virtual visit to the home of electrons. Well, I'll try to share the screen and I hope that everything goes well with respect to my PowerPoint and this goes okay. So is the PowerPoint clear now as a full screen?
You've just started sharing. Yes, it's visible.
Yes, sir. Yes.
It's on full screen. Is it okay?
Yes.
Perfect. So I will give my talk from time to time. There will be some questions that I will be asking, and anyone who would like to intervene may raise the hand and will be given the opportunity. And of course, if you think that I'm going too fast, you just let me know. I'll try to see what happens. So I'm pleased again to be part of this international webinar. So emerging trend in chemistry education and research. I'd like to thank all the organizing members for organizing this event. And today I'll be talking about a virtual visit to the home of electrons. This is one of my favorite talks because it gives me the chance to interact with the participants, and let's see how it goes. Well, I'm myself Ponajura Ramasamy from the University of Mauritius, but I'm also a visiting professor with the University of Johannesburg and Professor Extraordinarius with the University of South Africa. Thank you very much again for the introduction that you gave. Now, I always like to give this slide whenever I give a talk. Many times, wherever I go, there is always some question, where is Mauritius, right? So many people, they confuse it with Mauritania or they confuse it with Malaysia, but then but whenever you give a talk to Indians, I think this is not a problem. Most of the Indians, they are aware where Mauritius is. It is a small island in the Indian Ocean, and most probably you'll need a lens to see where is our small Mauritius on the map. Now, since I'm giving a talk to most of the participants coming from India, and of course, I understand that there are participants from other countries, I also like to share this slide, which is very interesting. A comparison between Mauritius and India. So if you try to compare in terms of area, Mauritius is about 2,000 and India is about 1,500 times larger in terms of kilometers square. And when we talk of population, Mauritius is about 1.3 million, whereas India is 1.35 billion. So you see, in fact, there is no comparison. You cannot compare Mauritius with India in many aspects. But of course, we share lots of commonalities. One of them is the cultural aspects with many Indians who came from India a long time back. Now, the next slide that I'd like to share with you, just I'll not take time on this about Mauritius. So if you, I hope that you can see the slide properly. So Mauritius is quite famous, I should say now, in terms of the beach and the sun and the sand also. But you see now with the issue of the coronavirus, the tourist industry has really gone down. But then there are some sceneries which are worth pointing out. Now, if you see this one, can you see the mouse moving when I use the mouse? Can you see it? When I move the mouse?
Yes, sir. Yes, sir. Yes, sir.
Thank you. So what we have here is a crater, a volcano. It is supposed to be a dormant volcano. It is known as Trocerf. And well, there are different schools of thoughts. Some of them thinking that it's dormant, some of them thinking that it's a dead volcano. But I really hope that it's dead, because if it is dormant, the day that it will erupt, Mauritius will disappear. Now, here we have a mountain, which is supposed to be known as the Le Monde Mountain. It is officially recognized by the UNESCO. And why it is recognized by the UNESCO is because in the past, when the slaves, they were trying to escape their masters, they went on top of, they were hiding themselves in the mountain. But then when their masters came and looked for them, they jumped to death. So many of them, they jumped to death. So that's why this mountain is officially recognized by UNESCO. Now, the next slide is about the University of Mauritius, because it's worth mentioning few points. Now, if you see down here, this was the University of Mauritius some 60 years back. It was almost the only building that was there. As you may have realized, Mauritius was dependent on sugarcane. So the faculty of that time was Faculty of Agriculture. Right, but then over the years now, we have, the university has expanded. Now it's a full-fledged university with several faculties, and we have a student population of about 10,000 in all the faculties, and about 1,000 staff across the different sections of the university. And of course, in terms of chemistry, we have about 300 students who are doing their undergraduates, their postgraduate, and their PhDs, and we are 10 staff in the department. Of course, it's not comparable as other colleges, I'm sorry, about other departments in India, like I can understand in terms of the science. But then myself, I am leading the computational chemistry group. And I may share with you that I started doing computational chemistry in almost 1996, right? Where we were using the Fortran language for our programming. And we were using at that time, supposed to be fast computers, but if you compare now, of course, they are very slow. So we were doing some computational work. So I did quite a lot in my postdoctoral research at the Delhi University. So when I was invited for the interview in 2000 at the University of Mauritius, there was no computational chemistry offered at the university at that time. So I was recruited basically because they considered it important that I developed computational chemistry. I should say that I've been quite successful over almost now 20 years, where we have a full-fledged module on computational chemistry at the undergraduate level, where the students, they are taught about the basics of computational chemistry, and then they apply it in their projects, in their MS, in their research, and so on. And now we are not only limited to Mauritius, but we try to share the knowledge to the African continent. Things are going on very well, and I'm very happy about the whole progress of computational chemistry in Mauritius and in Africa. So with this brief introduction about Mauritius, about the University of Mauritius, about computational chemistry, now I would like to overview the talk that I want to share with you today. Well, I'll be talking about the atomic orbital. I'll be talking about the molecular orbital. I'll be talking about the HOMO-LUMO. And then something might be new is the SOMO. And of course, I will be summarizing, and it will be my pleasure to address two questions which you may have. So is everything okay? May I continue?
Yes, sir, you can continue.
Very good. Thank you very much. Now, you see, let's take a fundamental question. Let's take a fundamental question. What is an atomic orbital? You see, in Mauritius, we at the 10th, students in 10th class, we do not have a local examination for them, but the students, they sit for the Cambridge International Examination. And this is one of the, I should say, famous question, which is given to the students at O level. O level means ordinary level. Comparing to India, this is the 10th class analog, right? 10th class. So they are given a typical question where they have the subatomic particles, namely the electron, namely the proton, namely the neutron. They are given the relative mass, they are given the relative charges, and they have to give the location. Now, for example, the proton, they may write the nucleus, the neutron, they may write the nucleus. Now, what do you think for an O-level student, for a 10th class student, is an expected answer for the location of an electron? Anyone would like to give an answer? I prefer to give the chance to the students. I think you have to raise your hand, mention it out, and the in charge will allow you to speak. Anyone? What do you think is an expected answer for the student at this level? Anyone? Yes, anyone? Yes? Anyone would like to give? The students?
Someone says around the nucleus.
Oh, no, maybe a bit more precise.
Few say around the in the orbitals.
No, but remember now, this is the most interesting part that I would like to start. Remember that in the 10th class, so maybe they are not too much aware of orbitals. Anyone more? No? Okay, so I will continue. So the expected answer for them here is the shell. So at that level, right, they learn about the shell. And for example, if you take the case of nitrogen, you end up with distributing the electrons. In the first shell, you have 2 electrons, and in the second shell, you have 5 electrons. So this is the situation at the 10th class level. But then what happens when they go in advanced level? Advanced level, most probably I'm talking about the 12th class, 11th and 12th class. Now, when you go to the A-level chemistry, now they start learning something more. They start learning about, right, here, atomic orbital. Now, what is an atomic orbital? Very simple, right? Now, an atomic orbital, if you allow me to read from the screen, an atomic orbital is a region of space around the nucleus of an atom that can be occupied by 1 or more 2 electrons. Now, I'll come back to what is an atomic orbital in itself, but then they learn at the A level, starting from the concept of shells, where they localize the electrons in a circle type. Now they start learning about not a localization, but a region in space. This is what they learn at the A level. And of course, they introduce about the 1s orbital, the 2s orbital, the 2p orbital, and so on and so on. That's very good. So moving from the shell, moving to a region in space. Now, what happens when they come to the tertiary level? Now, when they come to the tertiary level, now they start, some of the stuffs of quantum mechanics start coming up. Now, atomic orbitals are regions of space around the nucleus where an electron is likely to be found. Now, in a better terms, atomic orbital is a region in space where there is a probability of locating an electron. Now, let me take, for example, the 1s orbital. So if you take the 1s orbital, everyone knows that it looks to be a circle, but it is not a circle. What it is a sphere. Now, what is the physical interpretation of the sphere? For me, it's very simple. Think of you have a ball. If you have a ball, it has a three-dimensional surface. Inside the ball, it is empty. And of course, outside the ball, you have space. Now, if you consider the center of the ball as the nucleus, and you move along the radius to the surface of the ball, you're moving in an empty space. And of course, you'll reach the surface of the ball, and then again, outside the ball, it will be empty. Now, in quantum mechanics, everyone knows that what describes the state of a system, the wave function. Now, the wave function, unfortunately, it is just a mathematical expression, but then it does not have any physical meaning. What has physical meaning is the electron density, which is basically the square of the wave function. Now, if you take the ball, inside the ball at the center where you have the nucleus, the probability of locating the electron will be 0. There is 0 probability of locating the electron in the nucleus. As you move away from the nucleus, the probability for you to locate an electron increases. And when you reach the surface, this is the maximum region where there is the probability of locating the electron. And when you move away from the surface, the probability decreases. So this is your typical curve that you get, that we have learned about from quantum mechanics, about the phi square distribution, the probability distribution function. Therefore, moving from the shell, moving to a region, now we start talking about atomic orbital is a region in space where there is a probability of locating an electron. And of course, you relate it to the wave function, you relate it to the probability, which is phi square. I usually keep these slides, but I thought that we'll have a more larger crowd in terms of the knowledge. I did not want to put too much of the quantum mechanics. Now, what is next? Now, come to the quantum chemistry. So, if you allow me to read, an atomic orbital is a mathematical function that describes wave-like behavior of the electron. We all know that, for example, the 1s orbital of the hydrogen atom is represented by the wave function phi is equal to n e minus zr upon a. Remember that phi in itself does not have physical meaning, but then phi square, which is related to the electron density, this is related to the atomic orbital surface. Now things are improving. We have a better understanding in terms of quantum mechanics of the surface, of the electron distribution, of the probability of locating the electron. Now, what is a molecular orbital? That's very interesting. Remember that we moved from atomic orbital in terms of the shell. We have moved in terms of the region. We have moved in now to understand it clearly in terms of the wave function, but basically the electron density phi square. Now, if we limit to the broad definition, an atomic orbital is a region in space where there is a probability of locating an electron in an atom. Now the question comes, what is a molecular orbital? Again, I would like to give the chance to the students. So far, based on what I have tried to explain to you, who would like to give an idea about what is a molecular orbital. Now, maybe you have thought about it, but for me, it is very simple. For me, it is very simple. If we talk about atomic orbital is for an atom, very simple for us to realize that a molecular orbital is for a molecule. So, whenever we are talking about atomic orbital, we are talking about the region in space where there is the probability of locating an electron for an atom. When we are talking about molecular orbital, it is a region space where we can locate the electrons for a molecule. But it is much more complicated than what we can just see. But you see, things have evolved to such an extent that now you can use mathematics, you can use quantum chemistry, you can use the computational methods to have a better idea. Okay, so is everything okay so far? May I continue? Yes, may I continue, please?
Sir, can I ask you one question? There is Mr. Prashant Kamble has a question for you. Can I take that question now or after the?
It's up to you whether you want to take question now or later. It's up to you.
So we'll take it later. We will take later. Please go ahead, sir.
But is everything okay so far?
Yes.
Okay, good. Now the next thing now is right. How do we get the molecular orbitals? Right. Now, maybe if that takes you again back to your chemistry classes, maybe physical chemistry. Now, you'll realize that the molecular orbitals, they can be obtained by the combination of the atomic orbitals in the LCAO concept. Sorry. So what is the LCAO concept? The linear combination of atomic orbitals. Now, let us see how this goes and what will happen. Very simple. Now, let us suppose that we take your classical formation of hydrogen molecule starting from one hydrogen atom and the other hydrogen atom. Now, if you go back to your chemistry, you just I'm sorry. So if you draw the electron dot and cross diagram, so you end up with your simple diagram where you have the electron pair being shared. But quantum mechanics says something which is different. So what is that? This is something now which comes and it is difficult to understand, but then it may be simplified for students to understand. Now, surprising, if you take the 1s orbital of hydrogen atom and you take the 1s orbital of hydrogen atom, you get one bonding orbital and you get an anti-bonding orbital. But you see where this anti-bonding orbital is coming and why this is happening. Let us see now what will be next. So remember that I've started introducing the concept of the bonding and the concept of the anti-bonding. Now next, very simple. Why do we end up with the bonding and the anti-bonding? Remember that the electron is now being considered in the framework of quantum mechanics. It is being considered in the dual nature. So when it is dual nature, now we talk about particle, we talk about the wave. Now, let us suppose that this wave represents the 1s orbital, and then you have another 1s orbital of the wave. They may add constructively where you end up with this situation, but you can easily also realize that they may add up destructively, where now you end up with a zero situation. So now this gives you a physical interpretation of how the 1s orbital and another 1s orbital, they might end up giving the bonding situation and the anti-bonding situation. Now, maybe it is quite simple when you take the 1s orbital, but then the same logic applies when you go to the 2p orbital and so on and so on. But this is very important. The molecular orbital theory is very important. I will give you classical examples why this is the situation, and then we will see. So again, like I said, the two orbitals that they are adding constructively, they're adding destructively, leading to the sigma, leading to the anti-bonding sigma. Now, again, you may have the p orbital, which may add constructively, which may add destructively. So the wave type is a better understanding for you to see what is actually happening. But now, what happens when you start going into other systems? Remember that the case which I gave to you, remember that the case that I illustrated to you is for a simple 1s and 1s. But then what happens when you start going to other systems? I'm talking here of the Li2, the Be2, the B2, the C2, the N2, I'm sorry, the O2, the F2, and the Ne2. Now, if you try to work out the molecular orbitals, you'll find that most probably up to the nitrogen N2, things are okay. You can understand. But then as you move on, you'll find that something happens in terms of the relative distribution of the levels, and this becomes very important to explain the properties of the molecules. Now, how this is done basically with quantum mechanics in calculating the energy, but I will show you something using the computational methods. Now, I would like to share with you now the typical case for nitrogen and oxygen molecule. They lead to something which is beautiful, where you need to have a good understanding of the MO diagram, otherwise you end up in a problem. Okay, very good. Let us take the case of nitrogen molecule. Now, if we take the case of nitrogen molecule, so you have the 1s, which gives rise to the sigma and the antibonding, and so on for the pi, and so on, you keep on going. And now, if you distribute the electrons, it is okay, you're happy, all the electrons are paired, right? It basically satisfies your experimental observation. Now, what is that? I will share with you. Remember now, in such a system, all the electrons are paired. Now, I hope that you will be able to watch this video. I will start it. I hope that it runs. And if we need to repeat it, we will do that. So I can just start and we'll see whether it goes. Well, let me see. So here. So can you see that video? Is it okay? Can you see the video when I started? One person, yes?
Sir, I don't know about the others, but I cannot see your screen. And a couple of people are also saying that they are unable to see your screen.
Just a second. Okay, let me do it again. So let us pause the share. Now, I will start the sharing again. New share. Okay. So if I do this, maybe this share. So now, can you see now?
Yes, few people are saying it's visible on YouTube. Yes, visible. Some
Now,
are saying not visible,
okay,
but
some
some
of
are
them.
saying yes.
But how is that? So maybe if I
Many
do
saying not visible. Many saying not visible.
now.
Mr. Chetan?
Now,
Yeah. People are responding. Some
Sir,
saying yes.
for few people, yeah, Ashish sir,
Yes.
yeah, it's visible to us actually. Maybe, yeah, few people
okay.
are unable to view it.
Okay, but I cannot hear. Yeah, I cannot see.
Yeah,
Yes.
it is visible to everybody now. I think so.
Okay, now if I run the video, now let me try to see if I run the video whether it goes well. Now, can you see the video running now? Can you see the video running? So, did you see the video running?
Yes.
Okay, perfect. Now,
Yes, sir.
I will start it again. Now, what is happening here? So this is an experiment where liquid nitrogen is being taken as a liquid, and it is run through a strong electromagnet. Now, you need to concentrate and see. You need to concentrate and see. So nothing is happening as such in this region. So nothing is happening as such in this region. So I repeat the video. So here you have liquid nitrogen being poured on a strong electromagnet. And in this region now, basically nothing is happening. Now, why nothing is happening? Because the nitrogen molecule as such is diamagnetic. You have all paired electrons, and therefore you don't end up in any problem. Now, allow me to go to the next. Now, when we go to the next, all right, so, okay, before I go to the next now, I'm still with nitrogen molecule. Now, remember that we distributed the electrons in the molecular orbitals. All the electrons are paired, and therefore we could show that, we could explain that nitrogen molecule is basically diamagnetic. And now, no problem. We can use computational chemistry. We did a simple calculation at the restricted Hartree fork using the simple basis set, and we are able to obtain the molecular orbitals and distribute the electrons satisfactorily. There is no problem as such. Now, let us take the case of our dear oxygen molecule. The problem starts here. Now, if we refer to the valence method, where we have the electron dot and cross diagram, all the electrons are paired, and therefore the oxygen molecule has to be diamagnetic. Right? But then there is a problem. I will share now again the video where instead of pouring liquid nitrogen, now liquid oxygen is being poured. So can I continue? Is the video which I showed clear to you? Is the video?
Yes, people are saying yes.
Perfect.
Please continue.
Perfect. Now observe carefully in the region of the strong electromagnet. See what will happen now. So when you pour the liquid oxygen, now see this region, right? Now you will find something which is different. Yes. Now, can you see now that the liquid oxygen behaves differently? And this is because now it is paramagnetic. Okay, I hope you can see the difference in behavior when we had it with respect to the liquid nitrogen and now with liquid oxygen. This is different. Now, if the liquid oxygen or oxygen molecule is paramagnetic, this means that it must have unpaired electrons. So, very important, we have moved from nitrogen molecule being diamagnetic, but now oxygen molecule appears to contain unpaired electron as per the experiment, and therefore we have to see how to explain this. Now, this is how the help of the molecular orbital theory. If you still stick to your valence bond with the dot and cross diagram, you will not be able to have the electrons unpaired, so you have to do it with the MO diagram, where you end up with two unpaired, and therefore you can explain that satisfactorily. But then there is a trick in the computation. Remember that the calculation which I showed to you before, it was restricted Hartree-Fock. Now, if you repeat for oxygen molecule a restricted Hartree-Fock with oxygen, you will end up with all the electrons being paired, and the software has an issue to assign the 8th and 9th molecular orbital. The issue comes because you have unpaired electron and you cannot do the calculation with the restricted mode. For you to be able to get the required explanation, you need to go to the unrestricted Hartree-Fock method, where now you are able to obtain the required unpaired electrons. So then, I've been able to explain to you how we can have the molecular orbital, but then how we can use computational chemistry also to understand these types of electron distribution, but we have to be very careful with the calculation that we are doing. If we do the calculation blindly, we don't really understand what is going on, we may end up in a difficulty. Now, of course, now, if you want to improve your calculation and get it in the right way, the best method that you need to use, remember that for the oxygen, all the electrons were paired. You have two electrons in the pi antibonding which are unpaired. Then you have to use the restricted open shell calculation. If you use the restricted open shell calculation, you will end up with the situation that really explains your experimental observation. My idea here is you have to understand to use computational chemistry. It's not that you just do any calculation. Now, the next one, of course, you can extend to other systems. Let us suppose you extend to ethene. Now, when you extend to ethene, it's very simple. All the electrons are paired, and therefore your Hartree-Fock method, the default one, will give you the molecular orbital and the electron distribution. But then you learn about something now. The 8th molecular orbital is known as the HOMO, the highest occupied molecular orbital. The 9th molecular orbital is the LUMO, which is the lowest unoccupied molecular orbital. But now something more comes up. What happens when you take your NO2 molecule, which has one unpaired electron, and remember that it is better to use the restricted open shell HF method. Now, for you to be able to locate that unpaired electron, you need to use this particular method, and you are able to locate it. Now something new comes up, right? Remember that this is the LUMO, lowest unoccupied molecular orbital. This is the highest occupied molecular orbital, and now this becomes a new term, maybe to you, is the SOMO, singly occupied molecular orbital. It is very important, particularly when you are studying radicals, where you should be able to locate the SOMO. I will share one example, but I will not go into detail. But at this stage, remember that whenever you're working with radicals, you can't just any method. You have to understand what you are using. Now, let us suppose that we take a radical. Let us suppose that we take a radical and we end up in a situation where you have the HOMO and then you have the SOMO. But then when you add an electron, you may simply think that you simply add it here. And when you remove an electron, you may simply think that you remove it here. I'm taking an example where you have the HOMO and the SOMO. On removal of an electron, you can come here. When addition of an electron, you can come here. Well, these are the simplest situation. You'll be surprised to know that there are situations now where now you end up with the HOMO, which is higher than the SOMO, and now see possibilities for the addition of an electron. You may end up here, you may end up here, or you may end up in this situation. There might be others. If you remove an electron, you may remove an electron here, you may remove an electron here, or you can remove an electron here, and this one gets promoted to the higher. There might be other possibilities, and therefore you have to understand very well what you are basically doing. Now, in our lab, we have developed the method for studying the molecular orbitals of the simple molecules, the radicals, and we contributed to an important paper. So we contributed to an important, yes. Before I go to that, I would like to share the whole moral of our research project, the whole moral of our research group in my path over almost 20 years. Now, maybe here I would like to ask anyone, so who in a very short way knows about the rabbit and tortoise story and would like to share in the simplest form? Anyone? Anyone knows about the rabbit and tortoise story and would like to share? Anyone? Yes? Yes, please, anyone? Yes?
Yes. Ophila D'Souza is saying that slow and steady wins the race. Some also say slower one becomes winner. We should keep moving in life.
Okay, but maybe the version that you know is that you had the tortoise and the rabbit that they were competing. So the rabbit was so confident that he slept under a tree, and the tortoise came slowly and won the race. But maybe this is the version that we know from long way back. So allow me to share a video that gives a very strong moral, and I hope that you will be able to see. And if you can't hear the sound, you can read the caption, which will be down. Yes, I hope it works. Yes.
Once upon a time, a turtle and a rabbit had an argument about who was faster. They decided to settle the argument with a race. The turtle and the rabbit both agreed on a route and started off the race. The rabbit shot ahead and ran briskly for some time. Then, seeing he was far ahead of the turtle, he thought he'd sit under a tree for some time and relax before continuing the race. He sat under the tree and soon fell asleep. The turtle, plodding on, overtook him and soon finished the race, emerging as the undisputed champ. The rabbit woke up and realized that he'd lost the race. The moral of the story is that slow and steady wins the race. This is the version of the story that we've all grown up with. But our version of the story continues. The rabbit was disappointed at losing the race, and he did some thinking. He realized that he'd lost the race only because he had been overconfident, careless, and lax. If he had not taken things for granted, there's no way the turtle could have beaten him. So he challenged the turtle to another race. The turtle agreed. This time, the rabbit went all out and ran without stopping from start to finish. He won by several miles. The moral of the story? Fast and consistent will always beat the slow and steady. It's good to be slow and steady, but it's better to be fast and reliable. But the story doesn't end here. The turtle did some thinking this time and realized that there's no way he can beat the rabbit in a race the way it was currently formatted. He thought for a while and then challenged the rabbit to another race, but on a slightly different route. The rabbit agreed. The turtle and rabbit started off. In keeping with his self-made commitment to be consistently fast, the rabbit took off and ran at top speed until he came to a broad river. The finishing line was a couple of kilometers on the other side of the river. The rabbit sat there, wondering what to do. In the meantime, the turtle trundled along, got into the river, swam to the opposite bank, continued walking, and finished the race. The moral of the story? First, identify your core competency, and then change the playing field to suit your core competency. The story still hasn't ended. The turtle and rabbit by this time had become pretty good friends, and they did some thinking together. Both realized that the last race could have been run much better. So the turtle and rabbit decided to do the last race again, but to run as a team this time. They started off, and this time the rabbit carried the turtle till the riverbank. There, the turtle took over and swam across with the rabbit on his back. On the opposite bank, the rabbit again carried the turtle, and they reached the finishing line together. Both the turtle and rabbit felt a greater sense of satisfaction than they felt earlier. The moral of the story? It's good to be individually brilliant and to have strong core competencies. But unless you're able to work in a team and harness each other's core competencies, you'll always perform below par, because there will always be situations at which you'll do poorly and someone else does well. Teamwork is mainly about situational leadership, letting the person with the relevant core competency for a situation take leadership. And that is the end of the story.
Thank you very much. I hope that you could follow it. And the moral here is that this is what has been going on in the group. So teamwork, we believe, is very important. So I have students in the lab ranging from undergraduates to postgraduates. And we also have research collaborators across the world where we work as a team. So this is one of the publications that we ultimately, I'll show you, contributed, where if you want now to have details about the whole idea of the molecular electronic configurations. So this is a paper by Michel Coutet, which I really recommend to you. And this is the research project that we contributed, where there has been a reaction, the synthesis was done. They proposed a mechanism which involved a radical, and they had to know about the electron distribution, particularly in terms of the SOMO, LUMO level, and so on. Well, I'll not go into the detail, and ultimately this paper was published in Anguwante, and recently it has received lots of citation, and we received an communication from Anguwante that this work has been downloaded, one of the top downloaded in recent publication. So with this now, I would like to come to the summary of my talk. I have explained about the atomic orbitals. I have explained about the molecular orbitals, and then I will illustrate to you how to use computational chemistry. Of course, I've shared with you about our latest publication in Anguwante. Now, as a joke that I can share later, but then I would like to just mention about, we are organizing a virtual conference on chemistry and its application. You can check on the website, and if anyone is interested, we can still accept the abstract. This is a website that we have that describes the computational courses, and of course, I can't just give this talk without acknowledgement. I'd like to acknowledge the organizers of the webinar, Dr. Prabhu, the University of Mauritius, University of Johannesburg, University of South Africa, the Sigrid for the computations, and all members of the computational chemistry group. So thank you very much again. It will be my pleasure to address two questions. Thank you.
Thank you so much, sir, for a wonderful, wonderful lecture and a session. I hope you can take a glance at the comments that have come, and people have really, really enjoyed your talk on the virtual visit to the home of electrons.
Okay.
There are a couple of questions. Me and my co-moderator, Dr. Anand Burange, will take on a few questions. I will begin with the first. The first question comes from Mr. Mandeep Singh, and he says, if an electron is present in p orbital, then how it can rotate? Sir, can you hear me?
If an electron is?
If an electron is present in p yes. Orbital,
yes,
then how it can rotate in orbital or shell, as p orbital is dumbbell shaped and shell is circular.
Okay, allow me to explain a bit on this. Now, you see, I think the whole idea itself, that's why I gave this talk as a virtual. The whole idea of molecular orbital, the whole idea of electrons and so on is purely on a hypothetical basis. Now, let me go back to something which is simpler. For example, Einstein says that you have lights which consist of photons coming and so on and so on. But you see, this is something which is really something that has been proposed. It satisfies all the experimental observations, and therefore you accept. Now, my point here coming back is that an electron has a dual nature. It behaves as a particle and as a wave. So this is, don't think that there is an orbital there and the electron is spinning or whatever. For me, that all these concepts are purely virtual. Everything is because we consider these as okay because they are explaining the experimental observations. It may happen that in future that other experimental results come forward, and we will no more consider the electron to behave as we are considering them today. So having said that, thinking now that how the electron will move it's not a question of physical location. For me, it's only a question of virtual, and these are only explaining your experimental observation. I would answer it like this.
I hope Mr. Mandeep Singh is satisfied with your answer. I'll take one more question and then I'll ask Dr. Anand to take a few more. The next question is from Mr. Prashant Kamble, and he says, uncertainty principle suggests that electron cannot exist inside the nucleus. Then how one can justify the K electron capture process that we see in some radioactive elements?
Yeah, you see, again, as I'm saying, it comes back to the same thing. You see, there is no model, there is no modeling which is 100% perfect, right? So it happens that sometimes whatever model, for example, like you said, the electron cannot be found in the nucleus, zero probability. But then in quantum chemistry, you have all sorts of like departure from the normal quantum behavior, and people have come forward with proposed modeling, proposed theory that explain. So it may happen, of course, that in certain cases that this particular rule is not observed, and if you have a mathematical modeling and you have a proper modeling which explains satisfactorily the experimental result, this may be in agreement with everyone, but it may not be the perfect and 100% perfect one, in the sense that later you can find another theory that comes which contradicts this and gives a better explanation. I would again answer like this.
Over to you, Dr. Anand.
Yeah, yes, sir. Yes, sir. Sir, here is one question from an anonymous attendee, and he or she wants to know that what does positive and negative lobe in orbital
Yes, again, like
indicates? So
you see, like I've explained, these are only related to the, remember that when you're doing the calculation, like you have the low probability region and the high probability region. So these colored are only used to distinguish between these regions. And these are only for visual purpose, nothing else.
let me have one more question from Prashant Kamble. He asked that one question, that what condition makes SOMO to be lower in energy than HOMO? Can that be explained in a simple manner, or it is also like an elusive idea?
Yeah, very good. So now you see the whole inter-electronic interaction in the system, in the molecules, accounts for the relative ordering of the energy levels. Remember that the example that I've given to you is limited to like a simple binary system, but when you go to other systems having larger number of electrons, inter-electron interactions decide the energy levels, and which ultimately you have to use the proper method to be able to get something which is acceptable with respect to your experimental observation.
Okay. Mahalakshmi Nadar, she wants to know that are there any good, what are the softwares, computational softwares are available? Are there any links where we can download the software, and how? Yeah. So regarding that, she's asking.
Yes, so very good. So basically we use Gaussian, but if you don't have Gaussian, there is one software which is free but Linux based, which is Orca, where you can download, but it is not user friendly as it is for Gaussian. I will send the link for Orca. I will send the link for the computational chemistry group, and I will send the link for the virtual conference in the chat Zoom webinar.
So there's one more question. Dr. Google from Pune, he wants to ask, can you tell about application of MOT for coordination complexes?
Yes, again, like everything goes back to what experimental information, what experimental data you have, and to what extent you want to explain these experimental data. Sometimes it might be sufficient to use simple chemistry, simple logic to explain these results or these abnormalities or these data. But sometimes it might not, where now you have to adapt the methods, the computational tools to be able to satisfy the experimental observations.
So there's
Yes, sir.
one
Yeah.
more question. Yeah. Sir, can you address one more question if you
Yes.
don't mind?
No,
Yeah.
no, it's
Miss Kusum Chawla, she wants to ask, is there any modification of above principle, as here it is not obeyed?
Is there any?
Modification of above principle.
Well, it's not modification, but sometimes you find, again, due to inter-electron interaction, that it is not obeyed as we generally know about it, right? But again, how will you be able to identify that is what experimental results, what experimental data you have. But it's not 100% that it should be like this, it should be like this.
Yeah. Dr. Anand, can you take two more questions and I think
Yeah.
then we will conclude?
Yeah. Just one more question is there.
Yes.
It is about regarding the hydrogen, which term is better, whether means when you are taking hydrogenic atom or means or hydrogen like atom, so what is more relevant to use?
For which one, please?
See, electronic configuration of higher atoms are the strict in sense hydrogenic. So are the actual configurations of multi-electron atoms are so similar to the hydrogenic atom?
Well, again, like I've shown that in certain cases you can have the ordering changed with respect to the normal molecular orbital distribution that we have. And again, how we'll come to know whatever experimental results or experimental data that we have to adjust accordingly.
Okay. We'll take the last question for today's session. Why the difference in energies of the p orbital is observed beyond the YMO of nitrogen?
Again, it's only because most probably as you increase the number of electrons, the inter-electron interactions become more important, right?
Okay.
Than you have for example, when you have hydrogen molecule 2, if you take your lithium Li2 will be 6. So as the number of electron increases, inter-electron interaction will increase. So you might end up with more complex situation.
Thank you very much, sir. Ashish, sir?
Yes.
Yes, over to you, sir, actually. Yeah.
Yes, thank you, Anand. Ramasamy sir, thank you so much for your very, very simple, lucid, yet so very interesting talk on the virtual visit to the home of electrons. And there are many questions, those are still coming. So we would take these questions later and maybe email it to Ramasamy sir. So those who want the questions to be directed to Ramasamy sir. So would you take it on your email and you can answer those questions?
Perfect.
So
I will do that.
Yes, we will do that. Sir, and many congratulations to you on your achievement about your paper and the paper being rated one of the top downloaded. I think you deserve many more such laurels. And on behalf of the Wilson family and Association of Chemistry Teachers and also University of Mumbai, we want to say a big thank you to you for coming and gracing this occasion and setting the tone of this webinar. We are really grateful to you, and you have started the webinar, the international webinar, on a grand note. So on behalf of all the participants and the organizers, I want to say a big thank you, a heartfelt gratitude to you.
Thank you very much. Thank you again, everyone. It has been my pleasure, and I will follow the webinar. Namaskar, everyone.
Sir, and hope to see you in India soon. I think there will be many people who would want to block your dates. So
Sure.
we would want to see you soon in India.
If the whole thing settles, and I will come.
Thank you so much, sir. Have a wonderful day ahead.
Bye.
So, ladies and gentlemen, moving ahead now, without much ado, we will go to our next speaker.
Ask whether I am there.
And the next speaker is Professor G. Ramakrishnan. Professor Ramakrishnan is the president of Chromatographic Society of India, and he needs no introduction formally as such. But it's my duty to introduce Ramakrishnan sir. He is the former director of SIES Institute of Chromatography and Spectroscopy, Navi Mumbai, and past president of Indian Analytical Instruments Association. Professor Ramakrishnan did his PhD in organic chemistry on natural products from the Bhabha Atomic Research Center, another very prestigious institute, and the Bombay University, and was a research associate at Florida State University and Brown University, United States of America. He has had a very distinguished career in industry and has worked for reputed firms in India like the ICI, in Saudi Arabia, AMS, Kaki, and Arab Security Studies and Training Center, and in Singapore, the HB. He has served as Vice President of the Agilent Technologies and as Managing Director, Thermo Fisher Scientific. All the chemistry departments may definitely have one or two of the instruments belonging to these very, very prestigious institutes, organizations, I would say. He is a well-known, he is well-known for his scintillating talks on chromatography and spectroscopy, and in particular, mass spectrometry. He is consulting editor of the Globalized Research Journal of Chemistry, and he has a long list to add to. But in short, I could say that Professor Ramakrishnan is the chromatography man of India. So, ladies and gentlemen, let's hear Professor G. Ramakrishnan on his topic, Importance of Education in Chromatography and Spectroscopy at Graduate Level. Over to you, Ramakrishnan sir.
Thank you very much. I will upload the slides.
Are the slides visible, Mr. Chetan?
Yes, sir. Yes, sir. It's
yeah, unfortunately, my screen is blank, so I cannot see.
yes.
Is that screen visible now? Can people see the slides?
Yes, sir. Yes, sir.
Yes, many are saying yes.
Yes.
Okay. Thank you very much, Dr. Ashish, for introducing me. It's a great pleasure to participate in this international webinar on the importance of on the emerging trends in chemistry education and research, and especially being organized by Wilson College. I am indirectly and directly indebted to Wilson College for my education, during my education and during my professional career. I got interested in chemistry in the late 1960s and early 1970s, only due to Professor Kulur, L.R. Kulur, who came from Wilson College and joined SIES College as head of the department. He instilled the importance of chemistry and the way that we have to learn chemistry. So I'm indebted to him. And later on, recently, for the last 20 years, my association with the Dr. Prabhu, who is the General Secretary of Association of Chemistry Teachers, and me as President of Chromatography Society of India, had several interactions. We have worked together for the really betterment of education in India, and we hope to continue that all the time. So thank you very much, and thanks once again to the organizers, Dr. Sakina and the principal and all others in the committee, that this webinar has taken off extremely well. And with the introduction from the first talk by Dr. Ramasamy, and I'm the second speaker here, what I would like to talk to you is about the education in chromatography and spectroscopy. What is it that we should really focus upon in this field, which is a very important field? I will talk about the importance of chromatography and spectroscopy. And the way I am going to have designed this topic is a brief look at the science of the chemistry education platform, syllabus of BSc for chromatography and spectroscopy, overview of the importance of chromatography and spectroscopy in education, understanding the problem associated with the chromatography and spectroscopy education, and a case study at last, how we can address this. And if we are able to really multiply this, what we have done in one of the institutes, I think that will be very helpful in the all over India for the chromatography and spectroscopy education. If you really see that India is a very rich in education, I always considered, even when I was abroad, that thanks to India for instilling very good education in the universities and instilling the confidence in people that we are second to none. Wherever we go, we are able to really adapt to the conditions and pick it up very well and move forward. And that is why many people who are educated in India, when they go abroad, they become extremely successful. Though initially they will find it very difficult, but they are able to adopt it very well. And that the adaptation and the adaptation is very, very easy, that they do it very well. So if you see the universities, we have more than, these are little outdated slides, but you can say there are more than 350 universities, and deemed to be universities 123, central universities 47, private university 239, total 759. This may be getting close to 1,000 as of now. This is a few years old slide. Number of universities in Maharashtra, if you see, Central University 1, I think that should be referring to the IIT. State-run universities about 19, deemed universities 21. And science and pharmacy colleges under Mumbai University, there are 72 which offers BSc, MSc and PhD. And pharmacy colleges which go up to PhD level, there are 19. Now, if you see the syllabus, it's a very, very impressive syllabus. I think there is nothing that we can add to that. Almost everything is there. Introduction of chromatography, classification of chromatographic methods on the basis of phases involved, on the basis of mechanism and separation, planar chromatography, thin layer chromatography, principal technique and applications, paper chromatography, principal technique and its applications. You really see under gas chromatography for TY BSc, you will find that it is very exhaustive. Introduction, principle, theory and terms involved, instrumentation, block diagram and components, types of columns, stationary phases. In GSC, gas solid chromatography and gas liquid chromatography, detectors, TCD, FID, ECD, etc., qualitative and quantitative analysis and applications. Comparison between GSC and GLC. These are very important. This is almost a comprehensive as far as gas chromatography is concerned. Then in ion exchange chromatography also, there's quite a few in the introduction, principle, types of exchanges, ion exchange capacity, almost exhaustively talking about ion exchange chromatography. Especially if you go to HPLC, many of you are familiar with this. Syllabus is very exhaustive, introduction and principle, the components with their significance, solvent reservoir, degassing system, pumps, reciprocating pumps, pre-column sample injection systems, columns, and here you see advantages and disadvantages, UV visible and refractive index detector, qualitative and quantitative analysis. I say this is a very exhaustive syllabus, extremely good. There is nothing that we can think about adding. And of course, if you can add that a detector, you can add, which is an LCMS detector. I think that is probably also included later on. And in the thin layer chromatography, you can see both TLC as well as HPTLC. Again, you'll see that it is very exhaustive, the type of tensitometer detector, fluorometric detector, etc. If you go into spectroscopy, very, very good that it is starting with the electromagnetic spectrum, units of wavelength and frequency, UV visible spectroscopy, very exhaustive, including the chromophore, etc. And then mass spectrometry, basic theory, nature of mass spectrometry. And if you see, it's almost complete. Now, all education, if it is based on this, then it is a very thorough education on all these techniques. And if you go into IR spectroscopy, again, basic theory, nature of IR spectrum, selection rule, fingerprint region, and the NMR spectroscopy, basic theory of PMR, nature of PMR spectroscopy, delta, the chemical shift, etc. And the solvents used, anisotropic, everything, if you say spin-spin coupling, and if you do into all these type of applications of PMR into all these types of compounds, and problems and structural elucidation using UV visible, IR, NMR, mass spectrometry, everything. So it is very comprehensive, excellent. So when I am looking at our strengths and weaknesses and opportunities, I say that right from second year BSc, we start teaching chromatography and spectroscopy. Syllabus is expanded at the TY, BSc and MSc levels. Chromatography and spectroscopy is covered in every science discipline, including biology and biotechnology. It's a must common subject for all. And the colleges do have TLC, paper chromatography, column chromatography, etc. The weaknesses are the majority of the colleges do not have instruments such as the basic GC, HPLC, UV visible, FTIR, etc. Majority of teachers do not have the first-hand knowledge of these instruments. That means if the teachers are actually hands-on experience, then they would be able to teach the students in a much better way. And due to lack of exposure, students are not motivated in the subject. And the most important thing is that we need to have our young students motivated in chemistry. And the motivation comes from mainly the teachers who are completely involved. They are thoroughly knowledgeable about these techniques. And also when they are able to see how these instruments are functioning. Almost chemistry is a visual subject. There is a lot of, if you go into theoretical chemistry, there are a lot of things which cannot be visual. But when we go to this type of things, experimentation, it's a lot of visual things that you can do. So that will encourage the students to do better and to get interested in that. What we are interested in today's world is that how we can really motivate the students to take more and more science subjects and also to take some of the advanced subjects and to get them interested into research. So this is our challenge today. And without our preparedness for teaching chromatography and spectroscopy, which touches every part of our life, I don't think that we can get to where we want to get to. So what we need, all of us, especially in this area, in this coronavirus, COVID-19 has made it very clear that we want to have a healthier, cleaner, and safer life, a better environment for living. This can be the best timing for this topic in today's world. So definitely we want a healthier environment to live in. We want a very cleaner, that is everything to do with the environment, and healthier about the food and the drinks that we have, and a cleaner environment that we need, whether it is air, water, soil, etc. And safer. Safer also, we want a drug-free, and we want a crime-free, and we want all those types of problems or explosions, terrorism, etc. We don't want. We want a safer environment to live in. We want our family to be safe. We want our children to be safe. We want them to go to colleges and have very good education. Important to relate how this study affects our life. Now, the standard techniques in chromatography and spectroscopy, many of you are aware, and some of them I'll be talking today. Thin layer chromatography and HPTLC, the high performance TLC, column chromatography, paper chromatography, gas chromatography and liquid chromatography, capillary electrophoresis, supercritical fluid chromatography. This I am not talking about much today. Ion chromatography, hyphenated techniques are very important. As you know, that some of the chromatography is a separation science. We are able to separate the individual compounds from the mixture, and then we want to detect them, we want to identify them, we want to quantitate them, and they are done by some of the detectors. And we can combine with the GC with an FTIR, which makes it very powerful as an qualitative analysis. And then GC connected with an MS becomes very sensitive as well as confirmatory technique. And similarly, you can have HPLC connected with a UV visible and a direct detector, HPLC with FTIR, HPLC with a mass spectrometer, which is very, very popular today. And then you can have capillary electrophoresis with a mass spectrometer, SFC with a mass spectrometer. And in the case of inorganic analysis, you can have an ion chromatograph coupled with an ICP-MS. So these are the hyphenated techniques that is very much available today, and which is very important for us to understand what is available and what is the application. Now, this is a very important slide. This is where I say the chromatography and spectroscopy really touches our life. If you see really around, I constructed a slide mainly to drive home one thing, saying that consider this as an axle, chromatography and spectroscopy axle. Now, any chemical industry that you take, especially organic chemicals, you will find environmental industry is a very big industry, petroleum, petrochemicals, then pharma industry, essential oils, food and beverages, and you can polymers, you can keep on adding on this axle wherever you are working with organic compounds and organometallic compounds, you can expand this axle as much as you want and put a wheel around, then you can see the importance of chromatography and spectroscopy. So in principle, chromatography and spectroscopy, really the techniques touch our life. Everything that we do in a day, right from whether we are sleeping or awake or any time, chromatography and spectroscopy instruments are working all around the world to make sure that our three objectives are obtained, that is to healthier, cleaner, and a safer environment. That is where we are working with all these things. Very simple, just to give an idea about for people who are there, especially the students who are the beginners. It is very, I definitely know that there are a lot of students and I want to make it as interesting as possible for them. Now the chromatography, as I told you, is a separation science. So if you have an adsorbent here in a tube and then you load it with the two compounds, which is marked by a triangle and a square, and then you have a mobile phase to go through, and that separates the compound into two. So chromatography is nothing but a separation of the compounds between two phases. One is a stationary phase and one is a mobile phase, and that is called chromatographic technique. So this is important to have a stationary phase and a mobile phase, and your compounds undergo a separation between these two. Based on different principle, I'll be talking to you very soon about it. And then on the x-axis, you have the time or volume. This is called the retention time, and the area under the curve, you can say that is the amount of compound. It represents the amount of compound. So you can do it for both the qualitative analysis as well as quantitative analysis. In a GC, you can do the qualitative analysis if you have got a standard compound. Now in the mass spectrometry, even if you don't have a standard compound, you will be able to identify what are these peaks. So that is the advantage of connecting a GC to a mass spectrometer. And this is the detector signal. This is just a complete spectrum of all the separation techniques in general. So we have the column chromatography, which many of you are doing in your lab. And this started as early as in the early part of the 1900s, 1903, when Twisett did the separation of the plant pigments in a calcium carbonate, in a chalk powder with some solvents, petroleum either coming through. And that is how we know that the chromatography word was chroma and graphy, which is right. So we got these bands and we are still using this column chromatography. You can take it in a burette and do that. The simple thing is to fill some of the adsorbent like silica in a burette, and then you can start your separation using the organic solvents in an increasing polarity. So this is a plant extract, as you can see what is put. You can also have reaction mixtures to do this. Now you have a TLC here. Many of you would have used it, glass plate, put drops of your mixture and then start analyzing them by a mobile phase. So this is a stationary phase, which is a silica gel, and this is a mobile phase, which is a liquid, which can be a mixture of solvents also. Here also the stationary phase and a moving phase. So that is very important. So this is based on adsorption principle. Okay, and now then there is a paper chromatography that people put pigments here or amino acids here, and you can separate them using the solvent system that is loading on a paper. Now, paper chromatography does not depend upon adsorption principle, but it is more of a partition principle. Very important for people to note that the water molecules in the paper, in the cellulose, react as a stationary phase. And then you have a mobile phase. So it is a liquid-liquid interaction. Mobile phase is a liquid. The moving mobile phase is a liquid. Stationary phase is also a liquid, which is water. So that is a good example of partition chromatography. So not to get confused between TLC and paper chromatography. That's very important for you to remember. Now, when you go into gas and liquid chromatography, which is gas liquid chromatography and liquid liquid chromatography, in the gas liquid chromatography, you will find a liquid, a non-volatile liquid is a stationary phase inside the column, and a mobile gas is a mobile gas. So it is a partition taking place between the gas and the liquid. And in a liquid-liquid chromatography, you have the liquid phase, which is coated or bonded to a silica, and that makes a stationary phase. So liquid is a stationary phase, which is in the silica, and then you have liquid is a mobile phase, so that becomes liquid-liquid chromatography, which is a partition chromatography. So the most important thing is that you have to see that in the case of paper chromatography, in case of thin layer chromatography and column chromatography, it is based on adsorption principle, and all the other chromatography, it is a partition chromatography. So these are the two things I mentioned basically, the adsorption chromatography and partition principle. And here you have the normal TLC, HPTLC, and column chromatography. And here you have the gas liquid chromatography and liquid chromatography. A little bit further resolution. In gas chromatography, you can have a gas as solid as a stationary phase, for example, silica, which does not have any liquid coated to it at all. So that is purely an adsorption chromatography, gas solid chromatography, which is used in the separation of gases. Then the most popular, more than 95% that you use is a gas liquid chromatography, where the liquid which is coated onto inside of a column makes the stationary phase, which is a high boiling liquid, and then you have a mobile phase, which is a gas. So you have a mobile phase and a stationary phase. So that is called a partition chromatography, and here it is an adsorption chromatography. So these two are important for you to remember. In one is gas solid chromatography and one is gas liquid chromatography. GLC, which is further just simplified into GC. So today when you say I am using GC, most of the people assume that you are doing gas liquid chromatography, whereas liquid is a stationary phase and gas is a solid mobile phase. And as you can see, in the capillary columns are there. The capillary columns, the inside of the capillary is actually coated with this high boiling liquid. I'm sorry for the lack of time, I'm not able to show you the columns which are with me. I would have loved to show you the columns and how the columns work, but I think the time limitation will not allow me to do that. When you talk about liquid chromatography, again, the type of column chromatography that you are using, the solid is a solid phase is a constant, like in a column chromatography. You will find that you are packing the tube or a burette with a solid, and solid is a stationary phase, then liquid is a mobile phase. So that is again an adsorption chromatography, and that is a liquid solid chromatography, and that is based on adsorption principle. And in the case of liquid chromatography, you have the HPLC column, which is silica bonded with a liquid phase, high boiling liquid. And so that high boiling liquid like silicone oils, that becomes the stationary phase. And then you have the liquid mobile phase. So it's a liquid, which becomes HPLC, which is similar with the paper chromatography, which I explained to you. The moisture in the cellulose becomes the stationary phase in paper, and then liquid phase that you have, that is the liquid chromatography, which is based on partition principle. So if you find these two principles, I think you are well off. Now in the case of GC, again, you have got a mobile phase, which is a gas, and then you have a box here that you can see where you have got an injector and a detector and a column. This is really the gas chromatography instrument, and the column becomes the heart of the instrument, and this is where the separation takes place. Everything else is a supporting thing for this column. So if you don't have a good column and everything else is good, you cannot do a good GC. So make sure that your GC column is the correct one that you have chosen. Then you have an injector, you have a detector, and you have a column oven. You have to heat the column oven, which heats the column here, and then inject the sample here. It travels through the column and goes into the detector. You will be able to do the chromatogram. So this is a basic GC system. Now, if you want a GC-MS system, what you do is that here, when it comes out of the column, you connect that into a mass spectrometer, then it becomes a GC-MS. So this is separation accuracy. This is how the beautiful separation will get. If you have benzene, toluene, and orthoxylene and naphthalene, you will find that beautiful peaks are obtained here. The separation is excellent. So 1, 2, 3, 4, this is the solvent peak. The first one comes out here, a large peak, which is a solvent because you have dissolved your compound in the solvent. Then you can see benzene comes first, toluene, then xylene, and naphthalene. It depends upon their polarity. So benzene is the least polar that comes out first. Then comes toluene, then xylene, then naphthalene. So this is how you can separate your compound. And if you have your standard compounds of benzene, etc., you can really see this is called the retention time of benzene. It comes at around 1.9, I think. This comes at 2.5, the 3.02, and this comes at last around 9 minutes. So this is the minute scale here, retention time you can see here, and this is the concentration. So if the concentration of this is more, you will get a larger peak. The area under the peak will be large if this is small. So it is called area under the peak. You can do the integration and you can do the quantitation and you can find out how much is the actual amount present in the mixture. And that is the quantitation. One is the finding out what is the compound, that is called qualitative analysis. Then the next one is quantitative analysis, how much is there. So two things we are interested when we get a compound. One is what is it, that is called qualitative analysis, and how much is it, that is a quantitative analysis. Similarly, when you go into an HPLC, you can have a stack of boxes here, and you will find that the mobile phase is here kept on a bottle, and then you have the degasser. You have to remove the dissolved gases in the solvent. There are many reasons, because otherwise it will go and block. The air bubbles will go into the column, and that will create a big problem, and also the detector. Then you have the pump, which works at a very high pressure. Then this is the Gamble injector loop, and then this is the column oven. Here also you can heat the column if you want up to certain temperature. And then also you have to maintain certain temperature of the column. Today is very important that the pharmaceuticals and many of the regulated environment, they say you need to maintain the temperature of the column. So you cannot leave it under any room temperature. And then you have the detector. Detector can be different: UV visible, diode detector, RI detector, etc. There are many different types of detectors. Like in GC, you have FID, TCD, ECD, etc. In HPLC, you have UV visible, diode detector, which is also based on UV. And then you can have the electrochemical detector, and then you can have RI detector. You can have different types of detectors in HPLC also, which is very good. And also you can connect an HPLC to a mass spectrometer, which becomes a very, very powerful equipment to use for characterization. So this is basically a cutout of the diagram from the solvent system and to the pump and to the injector, etc., and to the column and to the detector. And there is the detector, diode detector. You can see the HPLC separation of paracetamol and phenacetin. Very good. I have taken just these two substances as an example to give you about different spectroscopy also. So you can see the separations are extremely good. And these are the structures, very similar structures in a way, because it is OH and it is OCH2CH3. Now, if you take also that, if you take a molecular space as such, very important to know all of them, all the compounds that you see cannot be worked on in GCO and GCMS. So only a small amount of portion here, which can have up to about, you can go up to a molecular weight of about 500, and then low polar compound, which are good for GC and GCMS. And if you go into other things, a high thing here, the non-volatile compound and proteins and peptides, etc., which are thermally labile, then you have to use them in HPLC and LCMS. So the thermally stable compounds, volatile compounds can be used in GC and GCMS, and non-volatile and labile compounds can be used with the HPLC and LCMS. And also in GCMS, you don't have too many selections of stationary phases, but when it, and also mobile phases. When it comes to HPLC, you can have innumerable number of stationary phases and innumerable number of liquid phase, mobile phase. And that makes it HPLC a very, very worthwhile technique today, much more versatile than GC. It's a little bit more expensive than GC, but it is more versatile than HPLC. So today you will find more of HPLC and LCMS being used around the world. But GC and GCMS has its own importance. You cannot take it away, because there are lots and lots of compounds which are low molecular weight compounds and which are volatile. For example, petroleum industry, for example, essential oil industry, and some of the volatile organics in water, etc. They can be done by GC and GCMS much better than LC and LCMS. In fact, some of those volatile compounds won't even do very well with LC and LCMS. You cannot even work with them. So they are inseparable. You need both GC, GCMS and LC and LCMS. So do not think that if I have an LC and LCMS, I don't need anything else. So that is not that you need all the type of things. So this is the GCMS. So basically from the GC, you will enter the compounds will enter into the ion source and they will ionize them and they will go into analyzer. Analyzer separates them according to their mass to charge ratio. So this analyzer is very important and it goes to the detector. Detector is electron multiplier detector. Okay, different from other detectors. And you must also see that is under high vacuum. So this, when I talk about spectroscopy, you must realize that mass spectrometer does not come under that electromagnetic spectrum. This is a separately different thing. This technique is by ionization. So mass spectrometry doesn't come under electromagnetic radiation. And it's a destructive technique, as you can see, when the compound enters the ion source, they are bombarded with electrons and they are destroyed. And the ions travel into analyzer. So that is the way GCMS works. So for you to make sure that you understand that, okay? But very powerful. You can get the structure of the molecules. You can do a library search. So your identification of the compounds, non-compounds will be much faster. And if you are working with unknown substances, you will be able to get the molecular weight and fragmentations, fragmentation peaks will help you in order to get some idea about the structure of the molecule. LCMS, again, very, very important. And the recent LCMS that you can see, they are done at the ionization is done under atmospheric pressure. So that is called atmospheric pressure ionization. So you can have choice of pumps and columns, etc. And it goes into the get separation over here. Here in the HPLC will separate it, send it to the ion source. They get ionized. The ions are injected into the mass analyzer. Separation takes place. They go to the HEDM electron multiplier and the detection takes place. And only these two are under high vacuum. In GCMS, you saw the ion source was also under high vacuum. There are many reasons. As you know, all these particular single topics will make at least 1 hour of presentation separately. So I am giving an overview of all these things very much. So when you go into paracetamol, you can get the structure here. You can find the ions here. This is the molecular ion, and then these are the fragment ions. And from this, you can get an idea about what molecule you are working with. And if you do not know how to arrive at the molecules, since paracetamol is a very well-known molecule, you can ask the computer to see whether this mass spectrum is present in the database of the computer, and the computer will, within few seconds, less than 5 seconds, will tell you the compound that you have on your hand is paracetamol. And similarly, phenacetin here, you can see 137, 108, etc. Okay, and you can see that the odd molecular weight here represents that there is at least 1 nitrogen present in that. If there are 2 nitrogens, it will be even. 3 nitrogens will be odd. It is called the nitrogen rule in mass spectrometry. So these are called fragment ions, and this last one that is called, that you normally see, is the molecular ion, and the fragment ions are actually formed from the molecular ion. So the complete display of molecular ion along the mass spectrum, along with the other fragment ions, is called mass spectrum. Now this is the mass spectrum of phenacetin, and this is the mass spectrum of paracetamol. Okay. This is one of my very favorite slides here, the electromagnetic spectrum. In fact, the syllabus talks about electromagnetic spectrum. So it is extremely important for people to understand, about this. One second. It's important for people to understand this electromagnetic spectrum. This is available in the internet, and you can see that this is the wavelength here, and this is the wavelength here. This is the increasing wavelength. So you can go all the way from picometers up to kilometers. Okay, then you can see this size of the molecules. What is the water molecule? There's the protein molecule, cell, etc., and almost like a soccer field here. And the most important thing that we have to understand is here are the gamma rays and the hard rays, X-rays, etc. And when the wavelength is very small, their energy is very high. That is where radioactivity and all that comes around this area, radioactive rays, X-rays, soft X-rays, etc. And when it comes here, this is our visible region. This is where we are in. And this is the ultraviolet region, this is the infrared region, then this is the microwaves, and this is the radio waves. So if you really see the ultraviolet UV spectrophotometer works in this region, wavelength here, and this is the visible region, that is the UV visible as you call, and this is the lamp you can see here. and this is the infrared region. This is where we do the infrared spectroscopy, and here you can do the microwave spectroscopy. This plus some of the Ramans you can do here, and then when you go into radio waves, you will be doing your NMR. And I said to you before, you will not find mass spectrometry anywhere. So please remember, mass spectrometry does not come under the electromagnetic spectrum at all. It is an ionization technique, and there is no absorption or emission involved. So once again, mass spectrometry, that's why we call it mass spectrometry and not mass spectroscopy. You can call UV visible spectroscopy, infrared spectroscopy, NMR spectroscopy, etc. But when it comes to mass spectrometer, that we say now the right way to call it is mass spectrometry. That is a measurement rather than it is working with any light energy. So I hope that is very clear to you today. And I think you must take this. I think this is what I say, that we need to have the right visual things. You need to have this, then we study from here. So this is when you really go into the UV visible, then again, we further go into what is the type of, the same thing represented here. So when you come to here, the visible region, ultraviolet region, infrared, etc., you can further resolve it for your understanding, microwave, radio frequency, etc. What is infrared region, near infrared, mid infrared, etc. So this, and then you can see that the nuclear power here, electronic excitation, vibration, rotation, and magnetic movement. So PMR, NMR, etc. is the magnetic movement. This is the rotational energy that you see here. Vibrational energy you see in IR. Electronic energy excitation you see in UV. See how beautiful it is. Once you are able to understand this, then it becomes extremely important to really have these visuals in front of you so that you can learn it. And this is basically the energy, the excitation. When you are talking about the UV, you need to have what is the sigma energy level, pi energy level, n bonding electrons, pi star and n star, and how these electrons get excited to the pi star and sigma star, very difficult, but pi to pi star is something that we see, and n to pi star. And that is what we normally see in our UV visible spectrophotometer absorptions. So it is, you have to understand that the chromophores, which have got really the n electrons, etc., they absorb much better in the UV region, and pi. So definitely if you have got a conjugated double bond, then you can see that there is a pi to pi star. If there is no double bond at all in a molecule, pi to pi star is impossible. Similarly, if you have got a ketone or an aldehyde, then you see double bond O, that O has got a non-bonding electron. The non-bonding electron can be excited into the pi star level. That is called the n pi star. So then there is an absorption. So once you have the right chromophore, then you will be able to see the UV spectrum. So without the UV absorbing chromophore, you will not be able to see the UV spectrum. And that is what, so by experimentation, you will be able to see, you have to use different types of compounds and to see the UV spectrophotometer and see whether you are getting any absorbance at all. And that becomes a practical study of spectroscopy. When you come to IR, again, you have to really understand when you go into a molecule level, what is stretching, what is bending, what is twisting, what is wagging, etc., rocking, etc. And that is very important to see whether it is a symmetrical stretch or unsymmetrical stretch, etc. And that is why the absorptions happens. And some of them are very high energy that is required for the stretching, and low energy that is required for twisting, rocking, etc. So by looking at the absorption spectrum, IR absorption spectrum, you will be able to tell what type of groups are present in that. Do you have a C double bond C? You have a C double bond O. You have a Benson ring. You have got a conjugated carbonyl to a Benson ring, etc., etc. So different groups, hydroxyl, for example, hydroxyl stretching, you will be able to see at a very high energy it requires. So around 3000 to 3200 to 3400 area, you will find centimeter inverse, you will find the hydroxyl and NH absorptions. So these are very important for us to know. So we are looking at UV at a molecular level. So they are called molecular absorption. And when you are going to, then you need a chromophore there. When you are talking about IR, then you are going to functional group level. And inside the molecule, you look at the functional group level and what is the type of stretching and bending and conjugation, etc., that is happening. So that is very important to understand what are this IR stretching, what are IR bending, what are the functional groups, etc., in the IR spectroscopy. So really UV gives you some idea, but IR gives you more about some of the functional groups. So when you take a UV spectrum, for example, again, I have taken the same example of paracetamol with this, very similar in nature. You will find that there is a lambda max around 243. Similarly, here also you will find it. And that is due to this absorption here, NH and then benzene ring, and then O attached, and then NH attached, and that chromophore will give you, and CO is a little far away. So CO absorption cannot be conjugated. If the CO would have been here, you would have got a tremendous conjugation and the absorption pattern will be quite different. Then you will get a 231, 272, 335, etc. You will get different absorptions if the chromophore is different. So this is a good one. So when you go into IR spectroscopy, here again, you will find what are the absorptions here. If you find a strong here, then you will find probably hydroxyls are present here in this region. And these are mainly CH stretchings. And then when you come here, around 1743, etc., you will find a CO group very prominent, and then you will have C double bond C in a benzene ring or C double bond C at this area around 1650, etc. And if there is a conjugation, then you will find the carbonyl shifting closer to these areas. So this area is extremely important. This area is extremely important, and this is the fingerprint region. There are different things. There are a lot of vibrations, a lot of rotational energy, etc. You can happen here, and stretching, as I said, stretching will come around here. And all of the rocking, bending, etc. will come over here. But the fingerprint region is very, very important, because when you take paracetamol anywhere in the world and you can overlap this, and if the fingerprint matches this, then you will say that it is definitely this. The different compounds have a different, very similarities in their spectrum. But unless the fingerprint region matches, you cannot say that it is the same compound. So two confirmative techniques are very important, are there in chromatography and mass spectrometry spectroscopy, and one is IR spectrum. It is a very qualitative tool, and another one is the mass spectrum, which has got a fingerprint. So in FTIR also we say it's a fingerprint region, and in mass spectrometer also say that is a fingerprint region. So you can see the confirmation. So in a court of law, we'll say that you need to do at least two confirmatory techniques. One is FTIR, another is mass spectrometry. This is the NMR spectrum. I cannot dwell too much onto this, but basically you can see, if you are familiar with, I have numbered it, methyl groups, and all the methyl groups you can see on the higher field near TMS, and you can see the doublets and triplets and quadruplets, etc. So once you interpret, then you will find it is very, very interesting. You can do PMR as well as carbon-13 NMR today, and both of them are give you powerful information into structural elucidation. So what are the causes and concerns? With the remaining time that I want to really talk about, what are our causes and concerns that I have, and I think many of the students have, many of the teachers have. What is it? Chromatography spectroscopy visual subjects, so practical is a must. So when you do practicals, as I said, people will get more interested. When you show a TLC, when you do a column chromatography, when you do a GC, when you do a HPLC, many of you are doing paper chromatography, many of you are doing TLC. So you can see you are so much interested in it. When you take turmeric powder and make a solution and put a spot, then you find 2 or 3 or 4 spots. You are interesting, you are seeing and mix 2 or 3 things, and you see that if they are not visible on the plate, put under the UV, you will find that they are UV absorbing compounds and giving you very good spots. So that becomes interesting. Or you can supply, so you can spray with sulfuric acid and heat it in an oven, then all these char compounds get charred. You can see the spots where they are. So that becomes a very practical, a visual subject. Now, as I told you, the university syllabus touches on theory, but not on practical, and does not insist on the infrastructure to support the practical. And that is a serious concern. And the colleges do not, this is not an allegation at anybody, please do not take me. This is my feeling that we should do really well. So this is applicable across the board. It is not to tell about one institute or another. It's across the board all over India. As I am traveling all over India and giving talks in colleges, I find this and I talk, they say the same thing. So my music is the same. It is not different at all. The colleges do not take interest in equipping the labs, though this is will increase the interest in the subject and competitiveness. Whichever laboratory I go, I see very, very rudimentary things in their lab. They want to see, show me, melting point apparatus or some other things, very rudimentary things and nothing sophisticated. And mainly this happens because lack of volunteers in the chemistry department would plead for this cause. Whenever I go to some chemistry department, I request one of them, please take interest, and you need to have a leader. You need to have one candidate who is interested in this so that he can take it forward. So the HODs may not be pushing for this with management. That is another thing. Management is not made aware that this is important. The research program grants do not make provision for buying these instruments sufficiently, or even if they are, once the grant comes, there are many other important things. So the importance of the chromatography or mass spectrometry or spectroscopy instruments take a back seat. So that is one of the problems. They are expensive. These instruments are expensive and they are expensive to maintain. But then the advantage that you get is more and more students get interested in chemistry and analytical chemistry. So no one is pushing for the interaction and collaboration of the instrumentation and chemical industry. It's very easy. India is a great country and there are many people who want to help the colleges. So if you go into chemical industries and say, we need your support, give your old HPLCs and old GCs there, many of them are willing to give it to you. So this is important in a pharmaceutical value chain. You teach the value chain and tell right from drug discovery, drug development, manufacturing, distribution, etc. Everywhere analytical chemistry is involved, mainly chromatography and spectroscopy. So once we talk about every stage, right from drug discovery, right from conceptual drug discovery molecule, right at every step, we need these things. And quality control, quality assurance everywhere. So if we put this in front of the students and teach them at every level, many of them are interested in going to pharmaceuticals, then this techniques becomes interesting to them. So this is a case study that I did. And there's a very old institute, SIS college, with analytical lab, and the old GC and HPLC when in around 2012, after my retirement, when I talked to them, we really started a small laboratory in the premises and SIS with the help of HPLC and GC donated by CIPLA. And then we developed, then the management also realized that there is a need for really setting up a much bigger lab. But the space was not sufficient in science, so we had to take it to SIS in Nerul campus and we built up there. And the management gave a space plus spent a lot of money in order to get some instruments. And we also worked with one of the industry champions like PerkinElmer to give some of their instruments. So thus we established the SIS ICS in 2013. So this was a small lab that we set up. We converted one of the very dumping ground where they had taken all the reports and other things, files was kept. We removed that and we kept these two instruments, HPLC and GC, which are still there. And we trained a lot of undergraduate students in this GC and HPLC here. And then when we started this, you can see that is where we moved into in the Nerul area. We built up a very big laboratory and we had a lot of instruments. We had the PerkinElmer GC, we had a GCMS with a headspace analysis, and then two HPLCs. This is from PerkinElmer and this is from Agilent. And then it's a closer look about the GC and GCMS, and this is the headspace analyzer. This is very important application when you have drunken driving. Then the blood is removed from this driver, and then it is put into a vial and heated, and the alcohol comes from here, goes through this elephant trunk into the injector and goes through the GC and goes to the mass spectrometer, and we can quantitate into the lowest levels in milligrams per milliliter of blood. And that is the type of work that can be done. And then this HPLC is a closer look, very high-end HPLCs, quaternary systems. This is the FTIR spectrophotometer with all the accessories, and then this is the UV visible. And many students who wanted to do their projects used to come and do their UV and IR spectrum here, and GCMS also for their projects. So the projects became much more worthwhile and a more, what I should say, very worthwhile reports in their projects compared to one without doing this, experiments. This is the ion chromatograph, which again got from Metron as a donation, and these are very expensive. So this is one technique, ion chromatography, which can do the cations as well as anions. Now, when you say cations, you can do a lot of elements by atomic absorption, but when it comes to anions such as CO3, NO3, etc., sulfates, etc., you cannot do that. So this becomes extremely valuable both for cations and anions, and this is what I called as ion chromatography. This you can connect to an ICP-MS also today, so you can have an inductively coupled plasma mass spectrometer coupled with an ion chromatograph. So that is extremely powerful. So you can see that these are the type of teachers. The advantage of this place was we gave a lot of importance to train the teachers. So we had teachers from almost all colleges from Mumbai as well as the rest of India many people who came even from Dehradun and many other places, and they underwent more than 110 teachers. We remember every year we used to teach about 20 to 30 student teachers, and then about a few hundred students and industry chemists have undergone. So these are the colleges which participated in sending their students for training. And the students who are getting, when they were at the master's level, we are giving them a hands-on training. So when they were at the GSC level, BSc level, we showed them how to work with the instruments. We showed them experimentation, how the sample is injected, how the peaks were coming out, all in GC, HPLC, GCMS, FTIR, etc. But when they were MSc and above, then they could really sign into a course and they will be getting hands-on experience, 2 days on GC, 2 days on HPLC, and 2 days on GCMS, etc. So that is the type of contribution we could make. And this made a huge difference in the teaching of this whole methodology. And this is what I want to propose to all the colleges and universities. Excellent syllabus is given. I think some experts have come out with a very beautiful syllabus. I cannot add anything to the syllabus. They are perfect. But what we need is really our effort to make sure that we equip our laboratories in order to give the best education to students and teachers. And these are some of the teachers who really learned from here, again, coming from different colleges, and they are all participated in the training. I don't remember which year it is. They're all college teachers. 1 week training we give, and they had some, morning will be lectures, afternoon they will be taking the hands-on training. And these are some of the students, and these came from SIS. They were the MSc and BSc students. Again, they are given a complete exposure to this instrumentation. This again, some of the students from, I think, this ICL College, Navi Mumbai, they are BSc students. They get complete exposure, and we give all the students the same level of exposure, same lectures. We give the lectures and they take them to the lab and then show them there. This is again one of the colleges, I don't remember. There's a title you can see. This is from the Rupert College, and again some of the teachers who brought all the set of students there, and they came. And also interesting is that many colleges after coming here, they also invite us and we go and give lectures into that. The rooms are full of students, and pin drop silence. They want to really learn. I really want to congratulate all the students and teachers who take so much of interest in chromatography and spectroscopy. And with that, I want to thank you. And I think I have taken exactly about 50 minutes or so. And if there are any questions or something, I'll be able to take some questions. But again, my sincere this one is that those students who are interested in chemistry, they must really contribute. There is no branch in chemistry today which can live without analytical instrumentation, and especially chromatography and spectroscopy. Me being an organic chemist, more interested in my PhD being in natural product chemistry, without this spectroscopic techniques, chromatography and spectroscopy, I don't think I could have finished any part of my research work. So we are heavily dependent upon chromatography and spectroscopy, and you can see everything that we see around, whether it is food analysis, pharmaceutical analysis, environmental analysis, drinking water, wastewater, and the air monitoring in the air. All these things are done by GCs, HPLCs, GCMS, LCMS, and coupled with the UR, UV, IR, NMR, mass spec. All these things are extremely important to us, and they are all should be close to our heart, and we must try our, and it makes our life interesting, and it makes our studies very profitable. And with that, I want to thank the organizers for giving me this opportunity, because I have a lot of passion about it. As you can see, I am committed to education in chromatography and spectroscopy. And if you have any question to ask, I'll be very happy to. I am no more teaching in SIS. I have left that 1 or 2 years back. So I think this director ICS should be removed. It's only Ramakrishnan.G, Chromatography Society of India. So please don't send any email to the first one. I will try to remove that from this slide. The department is still going on very well, and I'm very happy that that is established and many people are undergoing training there. Please, thank you.
Thank you so much, sir, for your very simple, lucid, yet very, very interesting talk on a topic which is very, very dear and near to all the teachers, because chromatography, this is in syllabus at all the 3 levels of the graduation program. And I'm sure that all the participants have been benefited by your talk. So we will take a couple of questions, and then I have some things to add to what you said. First question that I would like to take, I mean, I'll take the first two, and then Dr. Anand would take the next. Ms. Kushum Chawla says, her question is, in paper chromatography for separating cobalt and nickel ions, what is the role of rubinic acid? I repeat, sir, in paper chromatography for separating cobalt and nickel ions, what is the role of rubinic acid?
Good question, but I must apologize. I have not done inorganic chemistry separations using paper chromatography. All I have done is sugars and amino acids. So I will not be able to answer this question.
Okay, okay. Next question we have is from Mr. Rajesh Trehan, and he says whether MOSFET spectroscopy could be used in combination of chromatography.
Yes, that is what I mentioned. It becomes very powerful. If you connect a gas chromatograph to a mass spectrometer, it becomes GCMS. And GCMS is much more powerful than GC. Because in GC, what you happens is that you give two-dimensional information. On x-axis, you get the retention time, and on the y-axis, you get the abundance or concentration. But you cannot identify which are the peaks unless you have a standard compound. If you are analyzing benzene, toluene, xylene, then you need to have a standard sample of benzene, toluene, and xylene and inject them and see whether they are exactly coming at the same retention time. And even then I can ask a question, how are you sure about it? Some other compound could have come at the same retention time and the person will get confused. Whereas if you take a mass spectrum there, then you will find that the benzene mass spectrum will be 78 and the toluene will be plus 14, 78 plus 14, and the xylene will be the benzene plus you will have 28 to be added to that. So the molecular ion, you can see them and you can actually say which is benzene, toluene, and xylene. So that is the advantage of mass spectrometer. And if you are using HPLC, HPLC can be connected to a mass spectrometer. These are expensive. MS is expensive to connect to a GC. So GCMS is less expensive compared to an LCMS. LCMS is very, very expensive. But you can connect an LC into a mass spectrometer. Again, the mass spectrometer gives you all the qualitative analysis. You can really find out what is a molecular ion, which is very, very important in any molecule. In every molecule, what you really need to see first is, you will see, I want to see what is the molecular weight. First, you want to see the molecular weight. Then you want to go into a UV spectrum. Then you want to go to an IR spectrum. Then you want to go to an NMR spectrum. And if anything else. You can do elemental composition today, that will be good if you want to get an empirical formula. But if you get a high resolution mass spectrometer, you can exactly get your precise molecular weight. Also, you can get your elemental composition, your molecular formula. That is the advantage of a high resolution mass spectrometer. So you have low resolution mass spectrometer and high resolution mass spectrometer.
Thank you. Thank you so much, sir. Over
Yes,
to
sir.
you, Dr. Anand.
Sir, before moving to next question, actually the previous question, the Rajesh Trehan, he asked about is there possibility of combination of MOSBOR, not mass actually, MOSBOR with GC or with other chromatographic technique?
I have not come across MOSBOR being connected to a GC. So really, I've never seen that. So I don't know, many things are coming up. So I cannot say whether it is possible or not today. It may be possible. I don't know right now.
Okay. Sir, I will take another question from Rita Avasthi. So she asked that after the experimental work, getting the spectroscopic analysis of the sample, it's difficult task, smaller city. Okay. Are there any agencies or centers samples can be done?
I am losing your
analysis
no,
or
I cannot
HPLC
hear you.
analysis.
Sorry, I cannot hear you.
Hello?
Can you repeat the question?
Hello?
I cannot hear you. Can you repeat
Am I
the
audible
question?
now?
Yeah,
There is some tremendous disturbance.
Yeah. Am I audible now, sir?
No, we can't
No,
hear you, Anand.
there
We
is
can't hear
tremendous
you.
disturbance.
Am I audible now? Ashish, sir. You continue, please.
Yes. Yeah. Go ahead. You are audible. You are audible. Go ahead.
Okay. So Rita Avasthi has asked that are there any agencies or institutes where she can send GC or HPLC chromatograph samples for analysis? Want to suggest few institutions where analysis can be done?
Yeah, I think it depends upon your city, and they really heavily advertise that. As far as this Mumbai is concerned, I know there is a sophisticated instrumentation center in IIT, and they were doing this for a payment, and I think that is very subsidized for educational institutions and students. I used to do that when I was in SIES for students and teachers at a very subsidized rate, and for industries at a much higher price. But that I am not in control of that. I don't know who is doing that right now there. If they are able to do that, that'll be good. But there are many private or other institutions which are doing it. But definitely, I know in Mumbai, the IIT sophisticated instrumentation, it is called Analytical Instrumentation Center or so. So they were doing that. So you have to really inquire, which institutes are able to do that. And you can also check any of the nationalized laboratories such as NCL, ISAR, Pune, and different government institutes. When they have this facility, they are all asked to make some generating some funds. So they are all waiting to get some samples. So I think there is no dearth of sample analysis, but the only thing is a time factor. See, when you send a sample, you want the result immediately. And this goes in a line. And then when you get the results, nobody knows, and that is the problem. But if there is an institute nearby, and if you can take your sample there, and if you can sit and analyze that, that is the best thing to happen.
So there's another question.
It was much more difficult during my time, but fortunately I had BARC, and BARC was one of the best equipped laboratories in the country. I'm talking about the 70s. And so, it was one of the lucky guys to have all these instruments under one roof. Yeah.
Sir, Ansari Mujahid wants to ask that, is there any independent course in SIES for BSc and MSc pass students?
Can you repeat, what was that?
Is there any independent course in SIES for BSc and MSc pass students? Maybe wants to inquire
for the past students. You are talking about the
past student.
Yeah, you are talking about the students who have their BSc degree and MSc degree. Is that what you are talking?
Yeah. They have already passed their BSc and MSc. And is there any other course that they can take at SIES?
The courses that I used to announce when I was in ICS was open to everybody, and especially for people after BSc and MSc who are looking for a job. Because in any chemical industry, when you go today, first thing they will ask is, how will you separate this compound? What are the techniques you will use? What are the things you will do? So you tell me any pharmaceutical company or any company where you go, chemical company, when they go, and if chromatography and spectroscopy is not a question that they are asking, I will bet on it that they will ask. That will be their favorite question to ask. Tell me, how will you separate this compound? Tell me about chromatography. Tell me about spectroscopy. So if you are talking about the coursework, I think there is, if I remember, the one course that I am thinking about is the under Mumbai University in Kalina. That was the thing called Garware, I think Garware course. Please find out about that. They have the instrumentation course for BSc students and MSc after they complete it. And there is a 1 year or 2 year course that you can check about that.
Sir, actually, Ashish sir. Just I want to ask one thing. Other than QA box, in chat box, many people have asked, most of the people have asked the question that if they want to contact you as a faculty and they want their student to get expertise in area of chromatography, so how should they contact you? What is the general procedure, and what are the chances, how to get with it?
The best is to send me an email onto ramakrishnan.g@cromsauceindia.org, the one which I gave on the last slide. And you can easily go into website. There is Chromatographic Society of India website is there. And you can also post a question there that will come to me. And I am also arranging every week a seminar on Saturdays. So you can send this email and I will send it to you about the coming Saturday. It is going to be on GCMS applications into environmental and with the different accessories into mainly environmental analysis, essential oils and pharmaceuticals. And also the next Saturday, which is 4th of July, is going to be on orbitrap mass spectrometry. And on 17th of July, it is going to be on bioanalytical.
So there's a request. If you could share your email ID on the group chat, will you please share your email ID on the group chat or then flash the slide? Yes, sir. Yes, sir. Because of the shortage of time, now we are
I will do that
almost
right now.
5 minutes. Yes, sir. So thank you so much for talking about chromatography. And as rightly said, you are the chromatography man for us, for talking about healthier, cleaner, and safer environment, which chromatography is bringing to us, for discussing topic from right from the basics, that is the theory and principle of chromatography, to its application. And sir, if you could check the chat, all of them have said that your slides and your presentation was excellent. In fact, they are asking whether we could get your presentation. So in case participants, if we are able to get the PPT shared by the resource persons, we will definitely share it with you. So thank you so much for talking to us about how important chromatography is. How can we make it so interesting? I mean, a small thing like getting a turmeric powder and then performing it and arousing interest in students. I mean, thank you so much. I want to share with you, sir, that we at Wilson, we have our DST FIST lab, and being the DST FIST coordinator, I'm very proud to say that we house in a DST FIST lab equipments like the atomic absorption spectrophotometer and GCMS, both from Agilent. And we also have HPLC with fluorescence detector of Jasco company. And sir, it will be a very, very proud privilege if you could come to our lab, have a look at it and guide us, and also deliver a few lectures for us, our students, and we could make some arrangements and some short hands-on training program for other participants as well. One thing which is very, very important here to note that, sir, the charges for such courses is very, very exorbitant. I mean, I have not seen any course less than 5,000 rupees for an entire schedule. So I think that's one of the deterrent factor. So if we could somehow bring down the fees a little bit lower, I think all the teachers will be able to get benefit of these instruments and their applications. So, sir, can I take it a word from you that on our invitation, we'll give you a red carpet welcome at Wilson, and Prabhu sir and you could come and guide us with our equipments that are there, AS, GCMS, HPLC.
Yes, I will be very happy. In fact, I want to mention at this moment that a few years back, Dr. Prabhu arranged my lecture there and I had given. And at that time, I had raised this information. And I'm very happy that at the DST funding that you have got and you have equipped
Yes.
with all these instruments. And when I came there, these instruments were not there. So they must be
Yes.
recent additions. And congratulations to all of you. And that makes my heart feel good.
Thank you so much, sir. So on behalf of the Wilson family and the Association of Chemistry Teachers and University of Mumbai who are collaborating, we would want to express our gratitude and a big, big thank you to you, sir, for your presentation and for guiding us on chromatography. Once
Thanks
again,
very
from
much.
all the participants and from the organizers, sir, we say a big thank you to you. Moving on now, dear friends, to our very last session, which is going to be an interactive session. We have with us Dr. Shyam Rele from USA, who has joined us from USA, who is the Senior Advisor, Vaccine Translational Research Branch, DATES, National Institute of Health, Bethesda, United States. Dr. Shyam Rele is our alumnus. He's an alumnus of Wilson College, who I think is a through and through a thorough Wilsonian. He was in Wilson from 1988 to 95. That means his junior college and senior college both have been done in Wilson College. So we are very proud of our alumnus. Dr. Shyam had stood fifth in the merit rank at the university MSc exams, and he was one of the four who was selected on all India level for the prestigious Department of Atomic Energy Fellowship at the BARC, and he completed his PhD in organic and natural product chemistry from the Bioorganic Division, BARC, Mumbai. Dr. Shyam, after his PhD, received a prestigious fellowship to study abroad. He spent 5 years of his early research career training as the postdoctoral fellow at the Emory University School of Medicine, Atlanta, in the Division of Surgery and Bioengineering. Later, he was promoted as an assistant professor at the university. Post academia, Dr. Shyam joined the biotech industry as a senior scientist and conducted cutting-edge research, developing new products, processes, and core platform technologies for cancer, vaccines, and infectious diseases. He's got a very bright and illustrious biodata, I must say. He is considered as the subject matter expert in advanced nanotechnologies and drug delivery systems. He is in a critical position where he manages a complex, ladies and gentlemen, please hear this. He is in a critical position where he manages a complex $100 million portfolio of government contracts and development projects. A money man, I would say. He's got in his hands projects. He's a recipient of key scientific awards, and many, notably among them, are the Liquidia Technologies Annual Outstanding Scientific and Leadership Achievement Award, the Liquidia Technology Excellence in Innovation Prize Award. His leading of nanoparticle-based vaccine programs was funded for multi-million dollars by the Bill and Melinda Gates Foundation. He was also selected as the most promising early career scientist of Indian origin under 35 by the American Chemical Society. He currently serves as a network advisor, Maryland Technology Development Corporation. Not only is he into the corporate sector, he has also filed 3 patents and has more than 30 peer-reviewed publications and multiple presentations to his name. All work and no play makes Jack a dull boy is what we have heard, and we know this saying. But Dr. Shyam is also a very, very ardent sports person, and he is interested in cricket. While in Wilson, he was the captain of the Wilson cricket team, both at the junior and the senior college level, and he is right now making cricket popular in the United States of America, where I guess football and tennis are the major sport attraction. But as a new hobby now, in addition to sports and scientific pursuits, he is also a budding artist doing modern abstract art in USA, a modern abstract art. And he has his art been showcased in various galleries and exhibitions. Currently, Dr. Shyam stays in Washington, D.C., and as a normal human being, he loves lazing around, watching Netflix and Amazon, and at times is also having in his hand a glass of drink which may or may not have a alcoholic group present in it on a lighter note. And he loves his family time as well. And he has 2 basic philosophies in his life. And that's very important for the student who have joined us. The first is he feels that in life there are 2 options. Always choose the one that is right and that gives you peace. And do not choose the one that is easy and serves instant gratification. And the second philosophy is there is no substitute for hard work, perseverance, and determinations. With this brief introduction, ladies and gentlemen, I proudly present to you Dr. Shyam Rayleigh. Over to you, Dr. Shyam.
Yeah, thank you. Thank you so much, Ashish, for the kind introduction. This was pretty flattering to hear about myself, actually.
That's the truth.
But having listened to all the lectures, especially from Dr. Ramasamy and Ramakrishnan, I think it rekindled memories of my work as a natural product chemist and an organic synthetic chemist, the work that I did at BARC, and the parallels that I can draw from that particular experience too. So seems like we come from the same, I would say, school of thought for that matter, or for the schools where we had our training. But first of all, I want to thank Wilson College, especially Borde sir, Sakina ma'am. I saw the principal, Principal Nikhalje, I saw Sanjay.
Sorry, Dr. Sham, to interrupt you, but there are
Sure.
messages coming that would you please speak a little louder, or maybe the mic, if you could hold a little
Oh, sorry.
closer,
Can you
because
hear
there's
me
no
now?
audio.
Oh, sorry. Can you hear me now? Can you
A
hear me?
little more loud. Yeah.
Okay. Can you hear me? Okay. All right. Yeah. So I just was saying that, I want to thank the organizers for setting this up. This is an excellent, workshop, which gives an opportunity for students and potential future entrepreneurs and scientists and the scientific community to be a part of this particular discussion and understand what it really entails to get into the industry in any shape or form. But first of all, I want to thank, as I was saying earlier, I want to thank Borde sir for sure. Sakina ma'am, thanks for reaching out to me. Principal, Nikhalje. I saw Sanjay over there with his mustache and goatee after a long time. So nice to see Sanjay also, and Ashish, I'm seeing you or meeting you for the first time, and all the other Wilsonians. So who have joined this, or ex-Wilsonians who have joined this workshop. Just to, this is kind of, whenever I talk about Wilson, it takes me down memory lane. And because I have been a Wilsonian all throughout my life, 7 years of my life has been in Wilson, junior college, senior college, and then my master's. Also, I did in Wilson, and it rekindles a lot of memories. It brings back a lot of great memories and the times that I have spent. And just to be honest with you, whatever I am today in my career, or whatever little I have achieved or accomplished in my career, is mostly in part because of my teachers at Wilson and the time that I've spent at Wilson. It was great to see Prabhu sir also. I missed Prabhu sir also. I saw him after a very long time. But most of my formative years have been spent in Wilson, and subsequently that training and that learnings that I have had, I have kind of transitioned into. I went to BARC, and then from BARC to postdoc, and then subsequently now it's been 20 years in the US. But I think the foundation that took place was at Wilson, and I have to really thank, this is an opportunity for me to thank all my teachers who are there, who were there. I had a great time actually at Wilson. So I didn't, and I was talking with Borde sir a little bit about what I should present and what I should, because I didn't really prepare any slides per se. But maybe I will take some cues from where, Professor Ramakrishnan talked about all these instrumentations and all these technologies that are out there that need to be, when you're in college, typically, we study this, right? Means I've gone through this phase. A lot of people study it. Theoretically, they study it, but very few get an opportunity to apply, right? When you really start applying this, when you start really applying or start injecting HPLC samples, or start injecting gas chromatography samples, and then start analyzing the data, then you understand what it means, how the theory is translated into practice. So the question for the educators is, and I'm trying to push the envelope a little bit based on my own personal experience and based on where in US how students operate and what things are being done. Just to push the envelope, maybe the practicality of some of these things. If the students get exposure, if early on exposure, I think that would result in a much better understanding of the subject also, and much more engagement of the students. Because I think sometimes doing practical things has a larger impact than just studying theory out of textbooks. So matching the theory with the practicality, and it is very heartening actually when Ashish you mentioned that Wilson actually has all these HPLCs and GCs, which is fantastic actually, and it would be great if more and more people get an opportunity to train or at least understand the process, the different aspects of instrumentation, the different detectors that Professor Ramasamy talked about, what kind of detectors to use when, what kind of columns to use when, because each molecule has its own uh, a propensity or affinity for a different column or for a column material. And, and with everything that is going on in the world right now, especially on the COVID side of things, you know, there is a lot of product development in terms of pharma or vaccine manufacturing, and India is becoming an hub for contract manufacturing organization as a service sector, right? So all these aspects of instrumentation, uh, whether it's HPLC, mass spec, you name NMR, GC, these become very quantitative analysis for industry to analyze some of these compounds and some of these molecules and some of these products. And therefore, it becomes very imperative to learn them at an early stage and get engaged. When we were growing up, these things were not there, to be honest with you, and those resources were not there. Times were different. Means we are talking 20, 25 years back, 25 years back, resources were not there. Within the limited things that were available, Wilson was doing a great job, actually. The teachers were doing a great job. Only when we went out and when we went abroad that we started learning these things and understanding what that theory meant. So that lag that is there, that was there some years back or many years back, that lag in terms of understanding theory and applying that theory, was significant. But I think that lag can now be reduced or maybe on par with what is being done in colleges like Wilson and SIES and other institutes within Bombay. So I think this is great, but I think the opportunities uh, have to be created for everyone. And one of the reasons I'm going to say this is because I'm just going to push the envelope a little bit over here is that India as a country, the workforce is very young. And it is imperative for the educators and as custodians of education to ensure that the workforce is well trained, not just trained, but well trained, right? Because you're competing, you're going to compete with the world. It's not just going to be an India competition or competition for the jobs within India. You're going to compete across the world. So having a well-trained workforce is extremely important because I think that's where the focus should be.
Dr. Sham, can I again interrupt you?
Sure.
Your voice is very, very low. Can you somehow see to it that
Is
your
it
mic
okay
is a
now?
little bit closer?
Yeah. Can you hear me now? I don't know why
Or
it is
maybe you
low.
can turn off the video and then speak. Will that make some difference? Mr. Chetan, can you just guide him about how he can improve his sound quality?
सर अगर हेडफोन अगर आप यूज करेंगे तो चले, क्योंकि अगर वीडियो भी बंद किया तो भी आवाज नहीं आएगा. If you have a
Okay, let me
headphone,
try my headphone. Can you give me
yes,
one second?
yes, sir.
Yeah, please continue, Dr. Sham. Sorry for the interruption.
No. So those were my thoughts. But again, so I'm just going to touch base. Can you hear me now? Okay. Can everybody hear me, or some of you can only hear me? Some can't. Sakina, can you hear me?
No, everybody is can't hear, sir.
Oh, everybody can't hear me. Oh, I'm not looking at the chat either. Seems like
you're not audible.
Maybe I'm speaking in a softer voice because it's kind of 3:30 in the night over here. My family is already sleeping and snoring over here. So,
Sir, it's like a cricket stadium now and you go full ballistic, go full on, sir.
yeah. Give me one sec. Let me just connect. Are you able to hear me now?
Yes, sir.
Yes, much better. Yes.
Sir, abhi hello. Voice not
Now
coming.
and not coming.
Right now, yes.
Is it okay?
Yes, sir.
Yes, sir. Yes, sir. I think we have lost his voice again. Sir, we can't hear you. Is everyone please
still
there?
not audible. There are so many messages.
Dr. Sham, we cannot hear you at all. Dr. Sham, are you there? Dr. Sham, are you there? Well, till we get Dr. Sham online once again, may I request all the participants to not to worry about the feedback forms. We will be emailing you the link for the feedback tomorrow. Okay. So the full feedback for the entire webinar will be shared. The link will be shared tomorrow. There will not
Hi,
be
can you
any
hear me now?
feedback form today.
Can you hear me
Hello,
now?
Dr. Sham, are you there?
Yeah, I'm there.
Yes, please go ahead. We can hear you. Please go ahead.
Can you hear me? Okay.
Yes, it's better. We had lost you in between. Please go ahead.
Ashish, can you hear me?
Yeah.
Yes, we can hear you.
We can.
Please go ahead.
Sham, you can go ahead.
All right. So, the point I was trying to make is, I'll just stand over here and speak. I was trying to make is regarding the vaccine development effort, and the fact that so a lot of these instrumentations that or the materials that Dr. Ramasamy or Ramakrishnan talked about, those are applied also in the context of product development or drug manufacturing. Because when you go into the industry, while he touched based on the purification aspects of this particular product, those resins and those type of resins and those type of materials will be used to purify and manufacture a mass production of those vaccine components or different kinds of vaccine products that will be developed. So understanding the chemistry, so the point I'm trying to make is a larger point over here is that currently, for some time, there is nothing such as chemistry or physical chemistry or analytical chemistry. Everything is kind of interdisciplinary now. And because of the interdisciplinary nature of it, everything is connected. You need an organic chemistry needs help of analytical chemistry needs help of a computational analysis sometimes, and vice versa. And physical chemistry is also a part of that. And inorganic chemistry is also a part of that because you're talking about ionic interactions. So, multidisciplinary nature of the world is what science.
Still there is no voice.
No voice?
I think there is some problem with the setting.
My setting at my end?
Yeah. Yes. Yeah.
Okay.
It is low, but you are audible. It is low, but you are audible.
I don't know what is it. Let me check quickly. So this is okay over here.
Yeah, I think you can please go ahead, Dr. Sham.
Yeah, maybe he's. Can you hear me now? Okay.
Yeah. Little better.
So,
Sham, it's better. Go ahead.
Yeah. So I think that interdisciplinary nature has to be kind of inculcated in students early on, rather than thinking of it as an independent. Can you hear me?
Yeah.
Okay.
Yes, yes.
Okay, good. So I see some background noise actually.
Yeah, there is some background noise. I request everybody to please maintain silence.
Yeah, if somebody can mute, I think that will be good. Yeah, so understanding, I was talking about the interdisciplinary nature of it. I think of the work that is there currently conducted outside. I think that becomes very important for people to understand that one should not look at chemistry from a chemistry point of view, that this is organic or this is analytical. Myself, I passed out of inorganic chemistry. My PhD was in organic chemistry, and then my postdoctoral work was in biomedical engineering. Okay, so you make that transition, you use what you have learned and apply it into different areas, and the fields are so interdisciplinary that you will need the help of each and every subject and each and everything that you learn. So therefore, don't think that, oh, this is organic, oh, this is interesting, oh, this is physical, this is not interesting, I don't. But as you go and apply those principles, you will realize that it is so interconnected. And this is just the chemistry piece I'm talking about. But as you advance in your career in the chemistry industry or chemical industry or pharmaceutical industry or any other industry, you will realize that you will also need help of biology. You will also need help of microbiology. You will also need help of certain aspects of zoology. So there are so many things you are going to need help of to assist in your decision making and assist in your understanding of the subject. So I think, oh, there is still no audible. Can you hear me?
Yeah.
Somebody is saying not audible
Yeah,
on Zoom.
maybe the problem of the connectivity in that area. You go ahead, Sham.
Okay.
Go ahead. We can hear you.
But majority of you
Yeah,
can hear me.
majority of us we can hear it. Yeah.
Okay.
Yeah.
So so that's what I'm trying to address over here, just based on my prior experience, that one has to diversify also, and one has to learn multiple things to develop your own skill set in a marketplace. One of the examples I'm going to give you is of the vaccine development effort, right? A vaccine development, there are different kinds of vaccines that are being made for coronaviruses. There is a protein vaccine, there is a DNA vaccine, there is a RNA vaccine, there is what do you say, adenovirus vaccine, there is a ad vector vaccine. So my suggestion is, and again, this is more to the educators actually, that how are these vaccines made? This is not biology. There is a lot of chemistry involved. For example, for a protein-based vaccine, a cell has to produce that material, the protein. So there is chemical engineering that happens within the cell. You have to manipulate that engineering that happens within the cell for you to get a product out, which is a protein. Protein is a chemistry, but still it's a process of chemistry that is involved on a biological level. So understanding those aspects and understanding those, or incorporating those elements within the curriculum would be extremely beneficial for people to really understand the actual processes that take place, and they are ready when they really actually go into the industry. Because I don't think that training uh, is only available when you actually go into an industry, because a lot of this information can be proprietary, and therefore, at least the basic information or basic understanding of some of these things can be good for the students who want to venture into, this kind of an industry. And as I said earlier, CMO business in India is booming, and it's going to boom. And there are going to be these kind of skill sets that are going to be required. Multidisciplinary skill sets is what people are going to require. The other aspect, which I think should be included in the curriculum, I strongly feel should be included in the curriculum, because is emerging technologies. And if people are hearing this, maybe they can recommend to the higher ups also emerging technologies in terms of understanding nanotechnologies, nanoparticles, drug delivery systems, how these are used in the context of drug development, how these are analyzed, how these molecules are analyzed, how they self-assemble. How do you measure the particle size of this? There is a dynamic light scattering, and maybe Ashish, as you are kind of looking at instrumentation, maybe you should look at dynamic light scattering as an instrument, how to measure the particle size, how to measure the particle charge, and how those charges and sizes interact with the body, how they traffic in the body, where they go, depending on the charge, depending on the size. So that's a fascinating area again, that one should really invest in, and that's going to be the future. Gene therapies is another thing. Again, don't be afraid with the word gene. Gene means it's not genetic. Obviously, it is genetic, but there is a lot of chemistry involved in how you manipulate that gene, those gene therapies. So, though these are some of the technologies which are really rapidly advancing, and and I think India is lagging just in general. Probably industry is doing it, but from a curriculum point of view, also I think there may be some courses people are offering, but I think these courses should be integrated uh, within the existing curriculum with a practical application using HPLCs and using GCs and using mass specs to analyze. As again, Professor Ramakrishnan said, when you manufacture these products or develop these products, you have to have a certain quality control on those. You have to, you can only release those products in the market or can be tested in humans only if it meets a certain criteria, a certain requirement. And that requirement is extremely stringent. Okay, you can't have an analytical assay or analytical method that is not robust. You have to have a very consistent method. And how do you develop a consistent method? That's also a training. That is also a very important training. How do you develop those methods? How do you bring, how do you optimize those methods? Those become very imperative to advance your skill sets and work in an industry. So I would say that these are some of the things that one should really focus on from a, if one wants to really develop a career in this space. And I'm talking just based on my experience. A lot of things, as I said earlier, I started, I was a Wilsonian, all throughout Wilsonian. I learned my tricks in organic chemistry, natural product chemistry, and again Ramakrishnan talked about purification of natural products through column, enriching those, then characterizing those. That's a process, and understanding whether it's the right molecule or not. That's a process. But again, applying that understanding in a field that is completely alien to me, where I was working with material sciences, polymers. Again, polymer chemistry is chemistry, but it's a different kind of a chemistry, but understanding those aspects becomes very important. And how do you kind of then, build the gap or build bridges between these different fields becomes very important. If you, and as I said earlier also, it is very important to diversify, um, in your career at some point of time. If you keep doing the same thing, then you get bored, you get tired. But I think learning obviously there is a basic thing that you need to learn. And once you learn that basic thing well, how do you apply it into different areas of research, whether you want to do, drug development, whether you want to do vaccine development, whether you want to do material sciences, whether you want to do chemical engineering or something else, so each thing will require certain interdisciplinary, multidisciplinary back and forth between not just chemistry, but different aspects of microbiology, as I said, biology, biomedical engineering, material sciences, and that would then open the doors for different opportunities in different areas. Environmental sciences is there. There is pure chemical engineering that is there. There is green chemistry. Polymer chemistry is there. Means it can open doors to a lot of different variety of things. Biomedical engineering or biomedical sciences is one big area that people should focus on or think of. But when you are thinking of biomedical sciences, don't think of it as it is bio, it is medicine, and it is engineering. No, there is a big component of chemistry that is involved in biomedical engineering. Without chemistry, biomedical engineering completely collapses. So chemistry becomes the essence for sure, but it is equally supported by other things also. So just remember that as you are making your decisions. So I was just, these are some of my thoughts, and hopefully, young people who are attending this, I was like one of you when I was growing up, didn't know what to do or what direction to go in, but by through training and through other things that I have done, I was able to navigate the waters and achieve the success that I have achieved, or whatever little success I have achieved. So my suggestion to you, based on my personal experience, everybody's personal experience is different, but having stayed in the US for some time now, I think diversifying continuously and evaluating what are the new trends, and working on those new trends, getting training, becomes very equally important. I also understand the fact that those resources may be very limited, and may be very expensive, and not everybody may be trained. And therefore, it becomes very important for institutes like Wilson and SIES and other colleges, especially Wilson, which is so old and, you know, has been actually shepherding a lot of, spearheading a lot of these efforts in the earlier days to Dr. Prabhu and other people, you know, that they should try to, you know, do more of this training piece, you know, for students, for sake of the students. I remember when I was doing my MSc, or when probably my MSc, that 95 was the year when Prabhu sir started his MSc by research lab in the biochemistry room, or the biochemistry lab on the just above the chemistry lab. I think 95, 96 was the year when he started. Till then, we were just doing, you know, normal science at that point. In the earlier days, probably I have heard this. Before my time, there was some research being done in the earlier days in biochemistry and other in biochemistry labs. But that was before my time. When I joined, there was not much biochemistry. And then I know Dr. Prabhu was getting all the funds, or working with all the people in getting the funds to set up that lab. Amlani was there, Dr. Amlani was there, working with Dr. Prabhu for that. But again, I would, I mean, see, I'm a Wilsonian. I said, people want any input, any guidance, I'm happy to provide them. Borde sir has my email ID. You can WhatsApp me. I'm happy to provide you information in terms of what the trends are, where the technology is going, and help in any capacity I can. But again, I think having a much more broader perspective, not just a chemistry-based perspective, but a broader perspective of other areas, and having an appreciation for other areas would absolutely help the thought process, you know, and help you advance in your careers also. I think, yeah, those are my only things I think I would say. Uh, yeah, shoot questions. You know, I don't know. What else to say.
Yes, so anybody has any questions? In fact, if you see the chat, many of them are agreeing to what you are saying, Dr. Sham, and agreeing that, I mean, it is now not the time where we have watertight compartments, and training and practical training of all sort needs to be given to our students. So the participants are all agreeing to your experience and your suggestions.
Oh, that's great.
Yes. So, thank you so much. Thank you so much, Dr. Sham, for joining us all the way from the US, and sharing your experiences, your expertise, and talking about your alma mater, Wilson College. And thank you so much for all your best wishes. And we hope that next time you come to India, you come to Wilson College. So, ladies
No,
and
I always
gentlemen,
come to Wilson.
yes,
I'm always a Wilsonian at heart. So
yes,
I
once a
always remain the
Wilsonian,
Wilsonian.
always a Wilsonian. Yes, thank you so
Always a
much.
Wilsonian. You can't remove the Wilsonian from me. Never.
Absolutely, absolutely, absolutely.
But again,
So,
so Ashish, one last thing I would say. I just again want
yes,
to thank
yes.
you all for this opportunity. So again, thanks.
Yeah. So, I hope my video is unable. I mean, it's been disabled. Okay. So, ladies and gentlemen, here we come to the end of the last interactive session of today, of the 2-day international webinar. And I am sure you would agree that the title of the seminar suits very much with the kind of speakers we had. about emerging trends in chemistry education and research. We had the inauguration by a very, very senior faculty from Ireland who contributed in inorganic chemistry, inaugurating the session. We had a very interesting talk by Dr. Ramasamy talking about the minute particle, the electrons. Going ahead, then we had Ramakrishnan sir talking about a technique and its application about chromatography. And finally, to conclude, we had Dr. Shyam Rele speaking about the application of the science part to it. So thank you so much, all the speakers, and a couple of announcements before I call upon Dr. Sakina Bhutwala, the coordinator. Once again, reminding all the participants that the feedback link for the entire webinar would be shared tomorrow on email. And until and unless you submit the feedback form, the certificates will not be released because it's been attached to the feedback. The moment we receive your feedback, your certificates would be sent by email. So tomorrow, all participants kindly fill in the feedback form. Now I call upon Dr. Sakina Bhutwala to say a few words, and in case if there are any other announcements, I call upon Dr. Sakina Bhutwala. Over to you, madam.
Thank you, Ashish sir. Okay. Okay, can I
Yes,
start?
ma'am.
Yeah.
Yes, ma'am.
Okay.
Please go ahead.
Okay, good afternoon, everybody. The best and beautiful thing in the world cannot be seen or even touched. They must be felt by heart. Thank you is one such prayers among them. I consider it a great privilege to propose a vote of thanks to all dignitaries who have witnessed it as a memorable and successful event of the first day of the webinar. It would be a great privilege to thank to our beloved principal for all words of wisdom that radiated a source of energy within us. We will ever remain grateful to you, and we thank you for being with us today. I know that the success of the conference depends ultimately on people who have worked with us in planning and organizing both the technical program and in making the arrangement. Tomorrow, Professor Borde sir will formally give vote of thanks to everyone. But I like to acknowledge the strong and active support of our dear Prabhu sir. I like to thank Dr. D.V. Prabhu for his advice and brilliant suggestion in organizing the program, and without his motivation and help, this webinar would have not been possible. Heartfelt thanks goes to our respected speakers, Dr. James Barton, Dr. P. Ramasamy, Dr. Ramakrishnan, for the most interesting and informative session. I must mention our deep sense of appreciation to our alumnus, Dr. Shyam Rele, for sharing the important and valuable suggestion. I am very honored to be one making the closing remark and giving the vote of thanks in each such distinguished and intellectually stimulating gathering. Thank you very much to all the participants who have assembled here on this platform. I'm sure all present here will have a lot to take away from this today's session. A big thank you to Dr. Ashish Usgare and Dr. Anand Murange for his support toward anchoring of today's program and question answer session. I also extend thanks to technical support team and organizing committee for the enormous cooperation in the organization of this event. I thank you once again for being with us today. Indeed, it has been really a great pleasure. Thank you very much. See you all tomorrow at 10 a.m. tomorrow. Thank you.
Yeah, we will all meet tomorrow at 10 a.m. and the link for joining tomorrow will be shared on the Telegram. And that's the end for today, and we call it off a day. Right, ma'am?
Thank you. Yeah, thank you, Ashish.
Thank you. See
Thank
you
you,
all
everybody.
tomorrow.
See you tomorrow
10
at
a.m.
10 a.m.
Have a good day.